Welcome, everyone, to a journey into the heart of geological wonder. Today, we embark on an exploration of a place both breathtakingly beautiful and potentially, let's just say, dramatically impactful. We're headed to Yellowstone National Park, a vast expanse of pristine wilderness nestled primarily in Wyoming, but also spilling slightly into Montana and Idaho. Now, most of you will conjure up images of Old Faithful erupting, herds of bison grazing serenely in golden meadows, and maybe even the vibrant hues of the grand prismatic spring, and rightfully so. Yellowstone is a treasure trove of natural beauty, a testament to the power and artistry of the earth. But beneath this idyllic surface lies something far more profound, something that whispers of the planet's primal power. Supervolcano. The term supervolcano. It carries a certain weight, doesn't it? It evokes images of apocalyptic scenarios, of skies darkened by ash, and of a world irrevocably changed. And while such a cataclysmic event is thankfully rare, understanding the science behind supervolcanoes, particularly the one slumbering beneath Yellowstone, is crucial for appreciating the dynamic and sometimes volatile nature of our planet. So, what exactly is a supervolcano? Well, it's not your typical cone-shaped volcano that you might picture, like Mount Fuji or Mount St. Helens. Those volcanoes are formed by eruptions of lava and ash that build up over time, creating a familiar mountain profile. A supervolcano, on the other hand, is more of a geological complex. Instead of a single vent, it often features a large depression in the Earth's surface called a caldera. This caldera is formed by the collapse of the ground following a massive eruption. An eruption far larger than anything witnessed in recorded human history. Imagine, if you will, a vast reservoir of molten rock or magma lurking deep beneath the surface. This magma chamber is significantly larger than anything found beneath typical volcanoes, sometimes stretching for dozens of miles in length and width. As magma rises from the Earth's mantle, it accumulates in this chamber, building pressure over centuries, even millennia. When the pressure becomes too great for the surrounding rock to contain it, the result is, well, let's just say it's spectacular. But spectacular here carries a heavy caveat, asterisk, potentially devastating. A supereruption isn't just a bigger version of a regular volcanic eruption. The sheer volume of material ejected is orders of magnitude greater. We're talking hundreds, even thousands of cubic kilometers of ash, rock, and gas blasted into the atmosphere. To put that into perspective, the 1980 eruption of Mount St. Helens, a significant event in its own right, released about 1 cubic kilometer of material. A supereruption dwarfs that, dwarfing even the largest eruptions of historical times. And it's not just the volume of material that makes supervolcanoes so concerning. It's also the composition of the magma. The magma beneath Yellowstone is what we call rhyolitic, a type of magma that is rich in silica. Silica makes the magma very viscous, meaning it's thick and sticky. This stickiness traps gases, creating enormous pressure within the magma chamber. When that pressure is finally released, the eruption is explosive and violent, propelling ash and gas high into the atmosphere, where it can spread across continents and even impact the global climate. Now, let's circle back to Yellowstone. The Yellowstone caldera, formed by 3 massive eruptions over the past 2.1 million years, stretches across a vast area, roughly 30 by 45 miles. It's a testament to the immense power that lies beneath this seemingly peaceful landscape. And, yes, the idea of a supervolcano lurking beneath one of America's most beloved national parks might seem unsettling. But it's important to remember that volcanic activity is a natural part of the Earth's processes. It's a reminder that our planet is not a static, unchanging sphere, but a dynamic, evolving system, constantly reshaping itself through forces, both constructive and destructive. Think of Yellowstone as a sleeping giant. It's been relatively quiet for the last 70,000 years, a geological blink of an eye, really. But that doesn't mean it's gone. Scientists constantly monitor Yellowstone's activity, tracking everything from ground deformation and gas emissions to seismic activity and changes in thermal features. These observations help us understand the current state of the Yellowstone system and assess the potential for future eruptions. The key takeaway here is understanding the science behind supervolcanoes allows us to approach the subject with knowledge rather than fear. It empowers us to appreciate the incredible forces that have shaped our planet and to make informed decisions about how we manage and mitigate potential risks. So, as we delve deeper into the story of Yellowstone, remember that we're not just talking about a geological anomaly. We're talking about a window into the Earth's past, a glimpse into its potential future, and a testament to the enduring power of nature. Now, let's venture beneath the surface and unravel the geological secrets that lie hidden beneath Yellowstone's breathtaking beauty. Music gently transitions into the next section beneath our feet. Resting somewhat uneasily lies a geological titan. We know it as Yellowstone, but it's so much more than a national park teeming with bison and bursting with geysers. It's a window into the Earth's restless heart, a place where the planet's internal fires simmer just beneath a deceptively tranquil surface. To truly understand Yellowstone, we need to delve into its deep, turbulent past, a history forged in fire and shaped by colossal forces. The story of Yellowstone begins not with the park we know today, but with a geological phenomenon known as a hotspot. Imagine a plume of superheated rock rising from deep within the Earth's mantle, far below the crust. This plume, think of it as a persistent, fiery blowtorch, remains relatively stationary while the North American tectonic plate slowly drifts over it. As the plate moves, the hotspot punches through, creating a series of volcanic eruptions over millions of years. It's like trying to burn a series of holes in a moving sheet of paper, each hole marking a past eruption. The North American plate has been inching its way across this hotspot for roughly 17 million years, leaving a trail of volcanic breadcrumbs across what is now the Snake River Plain in Idaho. This plain, seemingly flat and unassuming, is actually a scar tissue of ancient volcanic activity. Each caldera, each valley, each subtle undulation in the landscape tells a story of fiery upheaval, of molten rock reshaping the surface. But how does this hotspot actually create a supervolcano? The process is complex, but it all boils down to the accumulation of magma. As the mantle plume rises, it begins to melt the surrounding crustal rocks. This molten rock, or magma, is less dense than the solid rock around it, so it starts to rise, forming vast chambers deep beneath the surface. These chambers aren't like giant, empty caves. Instead, they're more akin to a sponge, a network of interconnected cracks and fissures filled with partially molten rock, crystals, and dissolved gases. Over time, these magma chambers grow, fed by the relentless supply of molten rock from the mantle plume below. As the chambers expand, they put immense pressure on the overlying crust. The crust bulges and cracks, creating pathways for gases and fluids to escape, the very features we see today as geysers and hot springs. But the pressure can only build for so long. Eventually, it reaches a critical point. The magma becomes oversaturated with dissolved gases like carbon dioxide and sulfur dioxide, much like a shaken-up soda bottle. The crust above, weakened by the relentless pressure and heat, can no longer contain the forces brewing below. And then, the eruption. But unlike a typical volcano, which erupts from a central cone, a supervolcanic eruption is a much more cataclysmic event. The overpressurized magma chamber ruptures, releasing an enormous volume of molten rock, ash, and gas in a violent, explosive blast. The eruption doesn't just build a mountain. It obliterates the existing landscape. The ground collapses into the emptied magma chamber, forming a vast, bowl-shaped depression called a caldera. This caldera is the hallmark of a supervolcano, a visible reminder of the immense forces that shaped the landscape. And Yellowstone, of course, is home to one of the largest calderas on Earth. The Yellowstone caldera, Kea, as we see it today, is the result of 3 major supereruptions that occurred over the past 2.1 million years. The first and largest eruption took place 2.1 million years ago, creating the Huckleberry Ridge Tuff, a layer of volcanic rock that blankets much of the surrounding area. This eruption was so powerful that it ejected over 2,450 cubic kilometers of material, burying vast swaths of North America under a thick layer of ash. The second major eruption occurred 1.3 million years ago, forming the Island Park caldera, a slightly smaller but still incredibly powerful eruption. This event produced the Mesa Falls Tuff and further reshaped the landscape. The most recent supereruption occurred approximately 630,000 years ago, creating the Yellowstone caldera we know today. This eruption, known as the Lava Creek eruption, ejected around 1,000 cubic kilometers of material and formed the iconic Yellowstone landscape, including the Hayden Valley and the west thumb of Yellowstone Lake. But even between these massive supereruptions, Yellowstone has experienced numerous smaller but still significant volcanic events. Lava flows, hydrothermal explosions, and steam vents have all contributed to the park's complex and dynamic geological history. These smaller events serve as a constant reminder that Yellowstone is not a dead volcano. It's a living, breathing system, constantly evolving and changing. So, as you stroll through Yellowstone, marvel at the geysers and admire the stunning scenery. Remember that you're standing on the shoulders of giants, the geological giants of past eruptions. You're witnessing the ongoing legacy of a hotspot that has shaped the landscape for millions of years, and you're experiencing the surface manifestations of a vast and powerful volcanic system that continues to simmer beneath the surface. A system that holds the potential for future eruptions. It's a humbling and awe-inspiring thought, one that reminds us of the raw power of the earth and the ever-present forces that shape our world. The story of Yellowstone's formation is a testament to the Earth's incredible energy, constantly building, reshaping, and reminding us of our place in the planet's grand narrative. A narrative written in fire, ash, and the slow, relentless movement of tectonic plates. Now, let's delve into the fascinating anatomy of a supervolcano, focusing specifically on the engine that drives it all, the magma chamber and its intricate plumbing system. Forget what you think you know about regular volcanoes. These are on an entirely different scale, with mechanisms that are both terrifying and awe-inspiring. Imagine, if you will, a gigantic, partially molten rock body lurking several miles beneath the surface. This is the magma chamber, and in Yellowstone's case, it's not just one chamber, but rather a complex system of interconnected reservoirs, like a network of underground lakes filled with fiery, viscous goo. Now, let's be clear, it's not a hollowed-out cavern filled to the brim with lava like something out of a science fiction movie. It's far more complex than that. Think of it as a sponge, saturated with molten rock, crystals, and dissolved gases. This mixture, this magma, is under immense pressure, constantly trying to find a way to relieve the stress. The size of this chamber is staggering. Scientific studies using seismic waves to see beneath the surface suggest that the upper magma reservoir beneath Yellowstone is large enough to hold over 200 cubic miles of molten rock. That's enough to bury the entire state of Rhode Island under several feet of magma, and that's just the upper reservoir. There is likely an even larger, deeper reservoir that could dwarf the upper one. What makes this magma so explosive? Well, it's all about the composition. Yellowstone's magma is rich in silica, which makes it very viscous. Think of it like honey versus water. Honey is much thicker and stickier, right? Similarly, silica-rich magma resists flowing easily. This high viscosity traps gases like water vapor and carbon dioxide under tremendous pressure. These dissolved gases are absolutely crucial to understanding the potential for supereruption. Think of a shaken soda bottle. The dissolved carbon dioxide is under pressure, and when you open the cap, the pressure is released and the gas rushes out, creating a fizzy explosion. The same principle applies to Yellowstone's magma. Over time, magma slowly rises from the Earth's mantle, accumulating in these reservoirs. This process can take hundreds of thousands, even millions of years. As more and more magma enters the chamber, the pressure builds and builds. The surrounding rock, already under immense stress, begins to deform and fracture. Now, let's consider the plumbing system itself. This isn't just one single pipe leading from the mantle to the surface. It's a complex network of cracks, fissures, and pathways that magma uses to navigate its way through the Earth's crust. Think of it like a tree root system with countless branches connecting to a central trunk. These pathways are constantly evolving, changing as magma flows through them, widening some and sealing others. Earthquakes, both large and small, also play a role. creating new fractures and altering the pathways. The shallower portions of the plumbing system, closer to the surface, are particularly important. It's here that the magma can interact with groundwater, creating hydrothermal systems like the geysers and hot springs that Yellowstone is famous for. This interaction can also lead to phreatic eruptions, which are steam explosions caused by the rapid heating of water. The system isn't static, though. Think of it like a giant, slumbering beast, occasionally twitching in its sleep. Small eruptions, like the lava flows that occurred in Yellowstone several thousand years ago, represent minor releases of pressure. They're like letting off a little steam to prevent a much larger explosion. But what happens when the pressure becomes too great? What happens when the plumbing system becomes overloaded and the magma chamber can no longer contain the immense forces building within? That's when the potential for a supereruption becomes a stark reality. The trapped gases begin to rapidly expand, shattering the surrounding rock. The magma, now a frothy, explosive mixture, surges upwards through the plumbing system. The ground above begins to bulge and crack, a terrifying prelude to the cataclysm that is about to unfold. We're talking about an eruption that could dwarf anything in recorded human history. An event that would unleash unimaginable amounts of ash, gas, and rock into the atmosphere, with devastating consequences for the entire planet. Understanding the intricacies of Yellowstone's magma chamber and volcanic plumbing system is therefore absolutely crucial for assessing the risk and predicting future activity. It's a complex puzzle with many pieces still missing, but scientists are constantly working to improve their understanding. Using a variety of tools and techniques, seismic monitoring, for example, allows them to track the movement of magma beneath the surface. GPS measurements reveal subtle changes in ground deformation, indicating areas where the earth is swelling or sinking. And geochemical analysis of hot spring waters provides valuable insights into the composition and behavior of the magma. The more we learn about the anatomy of this sleeping giant, the better prepared we can be for whatever the future may hold. It's a constant process of discovery, a race against time to unravel the secrets of one of the most powerful forces on Earth. Now, shift our focus to what's happening right now at Yellowstone. Forget the deep history for a moment, and let's talk about the observable, measurable signs of life emanating from this sleeping giant. Because, despite its dormancy, Yellowstone is far from dead. In fact, it's teeming with activity, a geologically hyperactive landscape that scientists monitor with meticulous care. Think of it as a patient in intensive care, constantly hooked up to monitors that track every heartbeat, every breath, every subtle change. One of the most obvious and captivating signs of Yellowstone's ongoing activity is its remarkable collection of geothermal features. We're talking about geysers, hot springs, mud pots, and fumaroles, a kaleidoscope of bubbling, steaming, hissing spectacles that paint the park in surreal colors and offer a direct window into the Earth's molten heart. Geysers, of course, are the rock stars of Yellowstone. These eruptive hot springs, like the iconic Old Faithful, are powered by complex plumbing systems deep underground. Superheated water, trapped under pressure, suddenly flashes into steam, forcing a spectacular eruption of water and vapor high into the air. The frequency and intensity of these eruptions provide valuable data on the heat flow and pressure dynamics beneath the surface. Scientists closely track the timing and height of geyser eruptions, looking for any deviations from the norm that might indicate a change in the underlying volcanic system. A sudden increase in eruption frequency or a shift in the composition of the ejected water could be an early warning sign of increased volcanic activity. But it's not just the geysers that are telling us a story. Hot springs, those pools of scalding water that shimmer with ethereal beauty, are equally important indicators. Unlike geysers, hot springs don't erupt violently, but they constantly release heat and chemicals from the Earth's interior. The temperature, pH, and chemical composition of the water in these springs are carefully monitored for any changes. An increase in temperature, for instance, could suggest a surge in heat flow from the magma chamber below, and changes in the concentration of certain elements, like helium or sulfur, could indicate shifts in the composition of the volcanic gases being released. Mud pots, those bubbling cauldrons of thick gray goo, are another fascinating feature. These are essentially hot springs that are rich in clay and other minerals. The mud is formed by the alteration of rocks by acidic hot water and steam. The consistency and activity of mud pots can vary depending on the amount of water and gas present, and scientists monitor these changes for clues about the hydrothermal system below. And then there are fumaroles, vents that release steam and volcanic gases into the atmosphere. These are often found in areas where the ground is particularly hot and unstable. The composition of the gases emitted from fumaroles, including carbon dioxide, sulfur dioxide, and hydrogen sulfide, is closely monitored to assess the activity of the volcano. A sudden increase in the emission of these gases, or a change in their relative proportions, could be a sign of increased volcanic unrest. It's a delicate dance of chemical analysis and interpretation, piecing together the puzzle of what these gases are telling us about the deep Earth. Together, These geothermal features form a vast and intricate network of interconnected hydrothermal systems, all powered by the heat from the magma chamber below. By studying these features, scientists can gain valuable insights into the inner workings of the Yellowstone volcano and monitor its activity in real time. But beyond the surface manifestations, there's another crucial piece of the puzzle: ground deformation. The Yellowstone caldera is not a static landscape. It's a dynamic, breathing entity that subtly rises and falls over time, reflecting the changes in pressure and volume within the underlying magma reservoir. This ground deformation is measured using a variety of sophisticated techniques, including GPS, Global Positioning System, and INSA, Interferometric Synthetic Aperture Radar. GPS stations are strategically placed throughout the park to track the precise position of the ground surface. By monitoring these stations over time, scientists can detect even the smallest changes in elevation, down to the millimeter level. INSAR, on the other hand, uses satellite radar imagery to map ground deformation over a much wider area. By comparing radar images taken at different times, scientists can create detailed maps of the areas that are rising or falling. Think of it as a giant, space-based eye that can detect the subtle movements of the Earth's surface. The data from GPS and INSAR show that the Yellowstone caldera has experienced periods of both uplift and subsidence over the past few decades. Uplift, or rising, of the ground typically indicates an increase in pressure within the magma reservoir as magma or fluids accumulate beneath the surface. Subsidence, or sinking, of the ground suggests a decrease in pressure as magma or fluids are withdrawn. It's important to note that ground deformation is a normal part of Yellowstone's behavior and does not necessarily indicate an impending eruption. In fact, the caldera has experienced numerous periods of uplift and subsidence over the past few thousand years, without any resulting volcanic activity. However, significant or unusual ground deformation can be a cause for concern and warrants further investigation. A rapid rate of uplift, for instance, or a change in the pattern of deformation, could indicate a shift in the volcanic system and an increased risk of eruption. Scientists combine the data from geothermal monitoring and ground deformation measurements with other types of information, such as seismic activity, to create a comprehensive picture of Yellowstone's volcanic state. It's a complex and challenging task, requiring expertise in a wide range of disciplines, from geology and geophysics to geochemistry and remote sensing. But it's a crucial task as it helps us to understand the behavior of this remarkable supervolcano and to assess the potential risks it poses. So, while Yellowstone sleeps, scientists remain ever vigilant, listening to its subtle whispers and watching for any signs of awakening. Now, let's journey back in time, far beyond recorded history, to witness the monumental events that have shaped Yellowstone into the landscape we know today. We're talking about eruptions of unimaginable scale, events so powerful they reshaped continents and left their mark on the entire globe. Forget everything you think you know about volcanic eruptions, the kind you might see on the news. Dramatic as they may be, because what we're about to explore is on a completely different level. These aren't just eruptions, they're supereruptions. Yellowstone's history is punctuated by three truly colossal events. The first and oldest of the big three occurred about 2.1 million years ago. This eruption, known as the Huckleberry Ridge eruption, was the single largest volcanic event to ever occur in the Yellowstone hotspot's history. Imagine, if you will, a blast so powerful it ejected an estimated 2,500 times more material than the 1980 eruption of Mount St. Helens. Think of Mount St. Helens as a firecracker and the Huckleberry Ridge eruption as well, a planet buster. The ash cloud from this eruption blanketed a vast swath of North America, reaching as far as the Gulf of Mexico and even parts of modern-day California. It left behind the island park caldera, a gigantic depression spanning over 50 miles. A subtle but powerful reminder of nature's raw force. Fast forward about 800,000 years, and Yellowstone roared back to life with a Mesa Falls eruption around 1.3 million years ago. While smaller than the Huckleberry Ridge event, it was still a cataclysmic explosion, ejecting around 280 cubic kilometers of material. That's still more than 65 times bigger than Mount St. Helens, for reference. This eruption helped to sculpt the landscape of what is now Yellowstone National Park, contributing to the formation of the Henry's Fork caldera. And then, approximately 630,000 years ago, the most recent of Yellowstone's supereruptions, the Lava Creek eruption, carved the landscape we recognize today. This event, while slightly smaller than the Mesa Falls eruption, was still devastating. It spewed approximately 1,000 cubic kilometers of ash and lava, enough to bury entire states under many feet of debris. This eruption formed the present-day Yellowstone caldera, a sprawling depression that dominates the park's landscape. Now, what made these eruptions so extraordinary? It all comes down to the sheer volume of magma involved and the unique properties of the magma itself. Yellowstone's magma is rich in silica, making it incredibly viscous, almost like thick honey. This viscosity traps gases within the magma chamber, creating immense pressure. Think of it like shaking a soda bottle. only this bottle is miles wide and filled with molten rock under unimaginable pressure. Eventually, the pressure becomes too great, and the magma erupts in a violent explosion, shattering the overlying crust and sending ash and debris high into the atmosphere. But the impact of these eruptions extended far beyond the immediate vicinity of Yellowstone. The massive amounts of ash injected into the stratosphere had profound consequences for the global climate. This ash blocks sunlight, causing a dramatic drop in global temperatures, potentially triggering volcanic winters that lasted for years. Imagine the sun being dimmed, maybe even disappearing for days, weeks, or months at a time. These volcanic winters would have had a devastating impact on ecosystems around the world. Plant life would have struggled to survive in the reduced sunlight, leading to widespread crop failures and food shortages. Animal populations would have faced starvation and extinction, and the delicate balance of the food chain would have been disrupted. The human populations of the time, though much smaller and more dispersed than today, would have faced immense challenges adapting to these sudden and drastic climate changes. And it wasn't just the climate that was affected. The sheer weight of the ashfall would have collapsed buildings, contaminated water sources, and disrupted transportation networks. Imagine a world where the sky is constantly raining ash, coating everything in a thick, suffocating layer. Breathing would become difficult. Visibility would be reduced to near zero, and everyday life would grind to a halt. The geological evidence of these eruptions is scattered across North America, telling a silent story of unimaginable devastation. Layers of volcanic ash, known as tephra deposits, can be found hundreds, even thousands of miles from Yellowstone, providing tangible proof of the eruption's reach. These ash layers serve as geological markers, allowing scientists to date and correlate rock formations across vast distances. Furthermore, the eruptions left behind distinctive volcanic rock formations, such as rhyolite flows and obsidian cliffs, which are now iconic features of the Yellowstone landscape. These rocks, formed from the cooling and solidification of lava, provide valuable insights into the composition and behavior of Yellowstone's magma. The study of these past eruptions is crucial for understanding the potential hazards posed by Yellowstone in the future. By analyzing the size, frequency, and impacts of past eruptions, scientists can develop models and scenarios to predict the possible consequences of future volcanic activity. While we can't predict exactly when or how Yellowstone might erupt again, understanding its history allows us to better prepare for the challenges that a future eruption might bring. And speaking of the future, remember that Yellowstone is still An active volcanic system, constantly evolving and changing. The ground is still moving, the geysers are still erupting, and the magma chamber is still simmering beneath the surface. While the probability of another supereruption in our lifetimes is statistically low, the potential consequences are so significant that continued monitoring and research are essential. So, while we appreciate the beauty and wonder of Yellowstone's geothermal features, let's also remember the immense power that lies beneath, a reminder of the Earth's dynamic and ever-changing nature. It is a power that has shaped our planet for millennia and will continue to do so for eons to come. This understanding, this respect for the planet's raw potential, is essential for responsible stewardship and preparedness. And now, let us turn our attention to the present moment, to the rhythm of Yellowstone's rest. This immense caldera, this sleeping giant, isn't simply inert. It's breathing, albeit slowly and deeply. Understanding this caldera's breath, as we might call it, is crucial to grasping the true nature of the potential threat or lack thereof. So, what exactly is this breath? Well, it's the sum total of all the subtle, often imperceptible, activities that indicate Yellowstone's internal state. Think of it as the complex interplay of geothermal features, ground deformation, seismic activity, and even the chemical composition of its waters and gases. Each element tells a story, and together they paint a picture of a supervolcano in repose. Let's start with the most visible sign, the geothermal features. Yellowstone is, of course, world-renowned for its geysers, hot springs, mudpots, and fumaroles. These aren't just pretty sights. They're direct manifestations of the heat that still resides beneath the surface. The geysers, like Old Faithful, are particularly fascinating. They are essentially pressure valves, releasing pent-up steam and hot water in spectacular displays. But the timing and intensity of these eruptions can fluctuate, sometimes subtly, sometimes dramatically. Scientists carefully monitor these changes, looking for patterns that might indicate shifts in the underlying hydrothermal system. A sudden increase in eruption frequency or a change in the water temperature could be a sign that something is stirring deeper down. Then there are the hot springs, those shimmering pools of scalding water, often tinted with vibrant colors from the thermophilic bacteria that thrive in these extreme environments. The chemical composition of these springs is constantly analyzed. Changes in the concentration of certain elements, like chlorine or sulfur, can provide clues about the source of the water and the processes occurring deep within the earth. For example, an increase in the ratio of helium-3 to helium-4, two isotopes of helium, can suggest that more magma is degassing into the hydrothermal system. Because helium-3 is relatively rare in the Earth's crust and much more abundant in the mantle. An elevated ratio often indicates a deeper magmatic source, beyond the dramatic displays of geysers and the subtle chemistry of hot springs. There's the phenomenon of ground deformation. The ground within and around the Yellowstone caldera is constantly moving, rising and falling like the chest of a sleeping giant. This is due to the movement of magma and hydrothermal fluids beneath the surface. Scientists use incredibly precise instruments like GPS receivers and satellite radar to track these movements. These instruments can detect changes of just a few millimeters per year. The data gathered are then used to create detailed maps of ground deformation, which help scientists understand the underlying processes driving the uplift and subsidence. It's important to note that ground deformation is a normal part of Yellowstone's activity. The caldera has been rising and falling for millennia. Most of the time, these movements are slow and gradual, and they don't necessarily indicate an imminent eruption. However, a sudden or significant increase in the rate of uplift could be a cause for concern. It might suggest that magma is accumulating closer to the surface, increasing the pressure within the system. And, of course, there are the earthquakes. Yellowstone is a seismically active region with thousands of small earthquakes occurring every year. Most of these earthquakes are too small to be felt by humans, but they are constantly recorded by a network of seismometers that encircle the park. Like ground deformation, earthquakes are a normal part of Yellowstone's activity. However, a swarm of earthquakes, characterized by a sudden increase in the number and intensity of tremors, could be a sign of volcanic unrest. It might indicate that magma is moving upwards, fracturing the surrounding rock and triggering earthquakes. But let's take a step back for a moment. It's crucial to understand that all these indicators, geothermal activity, ground deformation, and seismic activity, are interconnected. They are all part of a complex, dynamic system. Changes in one area can affect the others, making it challenging to interpret the overall picture. Scientists use sophisticated computer models to integrate all this data and gain a better understanding of what's happening beneath the surface. These models can simulate the flow of magma and fluids, the stresses in the crust, and the potential for future eruptions. However, these models are only as good as the data that goes into them, and there are still many unknowns about the Yellowstone system. The key is to look at the trends and patterns over time. A single earthquake or a slight change in geyser activity is not necessarily cause for alarm, but a sustained increase in seismic activity, accompanied by rapid ground formation and changes in the chemistry of hot springs, could be a sign that something more significant is happening. Ultimately, understanding Yellowstone's current state of rest, its caldera's breadth, requires a multifaceted approach combining careful monitoring, sophisticated modeling, and a healthy dose of scientific skepticism. It's a continuous process of observation, analysis, and interpretation. And while we can't predict the future with certainty, the more we learn about this fascinating supervolcano, the better prepared we will be to face whatever challenges or peaceful slumbers lie ahead. Remember, Yellowstone is constantly talking, constantly giving us clues. We just need to listen and interpret what it is saying. So, how exactly do scientists measure the threat posed by a supervolcano like Yellowstone? It's not like they're sticking a giant thermometer into the magma chamber and waiting for the mercury to burst. Although, well, that would certainly simplify things. The reality is far more nuanced. Relying on a combination of sophisticated monitoring techniques and complex modeling. Think of it like this: Yellowstone is a sleeping giant, and scientists are constantly listening for its snores, monitoring its temperature, and watching for any signs of restlessness. The goal is to understand not just if it will erupt again, but when, how big, and what the consequences might be. And that, my friends, is no small feat. One of the primary tools in this geological toolbox is seismic monitoring. Now, you might think of earthquakes as a cause of volcanic eruptions, and sometimes they are. But more often, they're a symptom of what's happening deep underground. The movement of magma, the expansion of gases, and the fracturing of rock all generate seismic waves that can be detected by a network of seismometers strategically placed around the Yellowstone caldera. These aren't just your run-of-the-mill earthquake detectors. They're incredibly sensitive instruments capable of picking up even the faintest tremors by analyzing the frequency, intensity, and location of these earthquakes. Scientists can build a picture of what's going on beneath the surface. Are they seeing a swarm of shallow, high-frequency earthquakes, which might indicate the movement of fluids and gases closer to the surface? Or are they detecting deep, low-frequency earthquakes, which could signal the slow but steady rise of magma from the mantle? Each type of seismic event provides valuable clues about the volcano's internal state. But seismicity is just one piece of the puzzle. We also need to keep a close eye on ground deformation. Imagine inflating a balloon. As you pump air into it, the surface expands outward. The same principle applies to Yellowstone, albeit on a much grander scale. As magma accumulates beneath the surface, the ground above it can bulge upwards. Conversely, if magma is withdrawn, or if the system cools, the ground can subside. Scientists use several techniques to measure this ground deformation with incredible precision. One of the most common is GPS, or a global positioning system. But this isn't the GPS in your phone. These are highly specialized, permanently installed GPS receivers that can detect changes in elevation and position down to the millimeter level. By tracking these subtle movements over time, scientists can identify areas of uplift or subsidence and estimate the volume of magma accumulating beneath the surface. Another important tool is INSAE R, or interferometric synthetic aperture asterisk. This technique uses radar satellites to bounce signals off the Earth's surface. By comparing radar images taken at different times, scientists can create detailed maps of ground deformation over large areas. INSAR is particularly useful for monitoring remote and inaccessible regions like Yellowstone, where it would be difficult to deploy a dense network of ground-based instruments. It allows us to see the Earth breathing in ways that are simply impossible with traditional methods, beyond seismicity and ground deformation. Scientists also monitor gas emissions. Volcanoes release a variety of gases, including water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide. The composition and flux of these gases can provide valuable insights into the state of the magma chamber. For example, an increase in sulfur dioxide emissions might indicate that magma is rising closer to the surface, while changes in the ratio of different gases could reflect changes in the magma's composition or temperature. Scientists use a variety of instruments to measure gas emissions, including ground-based spectrometers and satellite-based sensors. They also collect gas samples directly from fumaroles and hot springs for laboratory analysis. This data helps them to understand the processes occurring within the volcano and to assess the potential for future eruptions. Now, all this data, the earthquake locations, the ground deformation measurements, the gas emission data, it's all incredibly valuable, but it's just raw information. To truly understand the threat posed by Yellowstone, scientists need to integrate this data into complex computer models. These models simulate the behavior of the magmatic system, taking into account factors, temperature, pressure, and the properties of the surrounding rocks. By running these models under different scenarios, scientists can explore the range of possible eruption outcomes. What would happen if the magma chamber continued to inflate at its current rate? What if a large earthquake triggered a sudden release of pressure? What if the magma's composition changed, making it more prone to explosive eruptions? The models can't predict the future with certainty, but they can help us to understand the potential risks and to prepare for a range of possible scenarios. And, of course, no discussion of Yellowstone's monitoring would be complete without mentioning asterisk geothermal activity. Sing Sing. The park is famous for its geysers, hot springs, and mud pots, all surface expressions of the vast geothermal system beneath. These features are not just tourist attractions. They are also valuable sources of information about the volcano's activity. Scientists monitor the temperature, flow rate, and chemistry of the geothermal features to detect any changes that might indicate volcanic unrest. For example, an increase in the temperature of a hot spring or a change in its water chemistry could signal that magma is rising closer to the surface. Similarly, changes in the eruption patterns of geysers can provide clues about the pressure and temperature conditions within the geothermal system. So, you see, it's a multifaceted approach, a constant and careful observation of a complex and dynamic system. It's about gathering as much data as possible, analyzing it rigorously, and using it to inform our understanding of Yellowstone's behavior. Are we completely safe from a future eruption? No. Can we predict exactly when and how it will happen? Not yet. But with each new piece of data, each new model, each new technological advancement, we are getting closer to understanding this sleeping giant and to preparing for whatever the future may hold. It's a long game, a marathon of scientific observation and analysis. But it's a game that is vitally important for the safety and well-being of millions of people. All right, let's delve into the realm of possibilities, the what-ifs that keep volcanologists both fascinated and, well, a little bit on edge. We're talking about eruption scenarios for Yellowstone, ranging from the relatively mundane to the stuff of geological nightmares. Now, it's crucial to understand that the likelihood of a massive caldera-forming eruption in our lifetimes is exceedingly low. We're talking about probabilities so small they're almost statistically insignificant. But almost isn't never. And understanding what could happen is vital for preparedness and informed decision-making. So, let's start with the most common type of activity we're likely to see at Yellowstone: hydrothermal explosions. These aren't magmatic eruptions in the traditional sense. Instead, they're essentially steam explosions caused by superheated water flashing into vapor. Imagine the immense pressure cooker that is Yellowstone's hydrothermal system. Water, heated by the magma chamber below, permeates the ground. If that water is suddenly depressurized, perhaps by a small earthquake or a shift in the surrounding rock, it can explosively boil, sending steam and debris into the air. These explosions can range in size from a few feet to hundreds of meters in diameter. They typically don't involve molten rock, but they can still be quite destructive on a local scale. Think of them like geysers on steroids. Areas with high concentrations of hot springs and geysers, like Norris Geyser Basin, are particularly prone to these events. While a large hydrothermal explosion wouldn't trigger a global catastrophe, it could certainly disrupt park infrastructure, damage nearby ecosystems, and potentially pose a hazard to visitors. Fortunately, these events are often preceded by warning signs, such as increased steam activity or changes in ground temperature, allowing for proactive mitigation measures. Moving up the scale, we have lava flows. Ow. These aren't your Hollywood-style fast-moving rivers of molten rock. Yellowstone's lavas are typically quite viscous, meaning they flow relatively slowly. Imagine thick, sticky treacle oozing across the landscape. These flows can cover considerable areas, burying vegetation and altering drainage patterns, but they typically don't pose an immediate threat to human life due to their slow pace. Past lava flows in Yellowstone have created vast basalt plateaus, shaping the park's distinctive landscape. If a new lava flow were to occur, it would likely be confined to within the caldera, slowly filling in low-lying areas, while potentially disruptive to local ecosystems and infrastructure. These eruptions wouldn't have significant global consequences. Next, we come to small to moderate explosive eruptions. These involve the eruption of magma, but on a scale far smaller than a supereruption. Imagine a volcanic vent opening up and spewing ash, pumice, and volcanic bombs into the air. These eruptions can create ash plumes that reach several kilometers in height, potentially disrupting air travel and affecting nearby communities. The ashfall can damage crops, contaminate water supplies, and pose respiratory hazards. The scale of these effects would depend on the size of the eruption and the prevailing wind direction. While not globally catastrophic, these eruptions would require a significant response effort to mitigate the impacts on surrounding areas. Now, let's address the elephant in the room, the supereruption. This is the scenario that captures the public imagination and fuels countless disaster movies. A supereruption is defined as an eruption that ejects more than 1,000 cubic kilometers of material. To put that into perspective, the 1980 eruption of Mount St. Helens ejected about 1 cubic kilometer. A Yellowstone supereruption would be 1,000 times larger. What would this look like? Well, picture this: a massive column of ash and gas erupting into the stratosphere, reaching tens of kilometers in height. Clastic flow. A searing avalanche of hot gas and volcanic debris racing across the landscape at hundreds of kilometers per hour, obliterating everything in its path. The immediate area around the eruption would be completely devastated. Ash would fall over a vast area, potentially blanketing much of the United States in a thick layer of volcanic dust. The consequences of a Yellowstone supereruption would be far-reaching and long-lasting. The ashfall would disrupt agriculture, contaminate water supplies, and damage infrastructure. Air travel would be severely impacted, and global supply chains could be disrupted. The eruption would also inject massive amounts of sulfur dioxide into the stratosphere, which would then react with water vapor to form sulfuric acid aerosols. These aerosols would reflect sunlight back into space, leading to a period of global cooling, potentially lasting for several years. This volcanic winter could have significant impacts on agriculture and ecosystems worldwide. Now, let's be clear. The scientific consensus is that the probability of a Yellowstone supereruption in the near future is very low. The geological record suggests that these events are rare, occurring only once every few 100,000 years. However, it's still important to understand the potential consequences so that we can be prepared to respond effectively if such an event were to occur. Scientists use sophisticated computer models to simulate different eruption scenarios, allowing them to assess the potential impacts and develop mitigation strategies. These models take into account factors such as the size and composition of the magma chamber, the rate of magma accumulation, and the prevailing wind patterns. These models can also help us understand the potential impacts of different eruption scenarios on specific regions. For example, a model might predict the thickness of ashfall in different areas, allowing us to assess the potential damage to crops and infrastructure. Models can also simulate the spread of volcanic gases, helping us to understand the potential impacts on air quality and human health. It's a complex undertaking, but these models are the best tools we have to predict what might happen and how best to respond. They help us answer vital questions like, where will the ash go? How thick will it be? And how long will the effects last? Ultimately, understanding the potential eruption scenarios at Yellowstone is about balancing awareness with perspective. While the possibility of a supereruption is undeniably concerning, it's important to remember that it's also exceedingly unlikely. The more likely scenarios, such as hydrothermal explosions and lava flows, while still potentially disruptive, are far less catastrophic. By understanding the risks and preparing accordingly, we can ensure that we are ready to respond effectively, no matter what Yellowstone throws our way. And remember, Yellowstone is constantly monitored. A vast network of sensors are constantly watching, listening, and measuring, giving us a vital early warning system. Now, let's brace ourselves because we're about to dive into the deep end. What if Yellowstone did erupt in a massive, supervolcanic event? What would be the global fallout? It's a scenario that's easy to dismiss as Hollywood fiction, but the geological record tells us it's a real possibility, albeit a remote one in our lifetimes. So, let's explore what that reality might look like. Firstly, let's be clear. A Yellowstone supereruption wouldn't be like anything we've experienced in recorded history. The sheer scale of destruction would be almost unimaginable. We're talking about an event that could dwarf even the largest volcanic eruptions of the past few centuries. The Tambora eruption in 1815, which caused the year without a summer, would seem like a minor inconvenience in comparison. The immediate impact zone, within a radius of perhaps hundreds of kilometers from Yellowstone, would be devastated by pyroclastic flows, searing hot avalanches of gas and volcanic debris that would incinerate anything in their path. Forget about towns and cities. We're talking about a landscape utterly transformed, buried under layers of ash and pumice. But the truly global consequences stem from the vast quantities of ash and gases injected into the atmosphere. Think of ash not as the soft, fluffy stuff that settles on your furniture, but as tiny fragments of rock and volcanic glass. These particles would be lofted high into the stratosphere, carried by prevailing winds across continents and oceans. And it's here, in the upper reaches of the atmosphere, that they would wreak havoc on a global scale. Imagine a hazy, perpetual twilight descending upon vast swaths of the planet. The ash cloud would block out sunlight, causing a significant drop in global temperatures. Some scientists estimate that a Yellowstone supereruption could trigger a volcanic winter, with average temperatures plummeting by several degrees Celsius, perhaps even more in some regions. This could last for years, disrupting growing seasons and causing widespread crop failures. The impact on agriculture would be particularly severe. Imagine trying to grow crops under a thick blanket of ash with reduced sunlight and cooler temperatures. Many agricultural regions would become unproductive, leading to food shortages and potentially widespread famine. International trade routes would be disrupted, exacerbating the problem as food supplies became scarce and expensive beyond agriculture. The ash cloud would also disrupt air travel. Jet engines are incredibly sensitive to particulate matter, and even a small amount of volcanic ash can cause them to fail. A Yellowstone eruption could ground air traffic for months, if not years, as airlines struggled to find safe routes and develop resistant engine technology. This would have a huge impact on the global economy, disrupting supply chains and isolating communities. But the consequences wouldn't be limited to ashfall and temperature drops. The eruption would also release vast quantities of gases, including sulfur dioxide, into the atmosphere. These gases would react with water vapor to form sulfuric acid aerosols, which would further reflect sunlight and contribute to the cooling effect. They can also lead to acid rain, damaging crops and ecosystems. Furthermore, supereruption could trigger a cascade of other environmental consequences. The sudden cooling of the planet could disrupt weather patterns, leading to more extreme weather events such as droughts, floods, and severe storms. Sheets and glaciers could expand, further reducing the amount of sunlight absorbed by the Earth and exacerbating the cooling effect. The oceans would also be affected. The influx of ash and nutrients could trigger algal blooms, disrupting marine ecosystems and potentially leading to dead zones. Changes in ocean temperature and salinity could also affect marine life, leading to widespread migrations and potentially extinctions. The social and economic consequences of a Yellowstone supereruption would be equally profound. Mass displacement of populations from the affected areas would create huge refugee crises. Infrastructure, from power grids to water treatment plants, would be overwhelmed by ash and debris. The cost of recovery would be astronomical, potentially bankrupting entire nations. In addition to the direct impacts, there would also be significant psychological effects. Imagine living in a world shrouded in ash, with food shortages, economic collapse, and widespread uncertainty about the future. The stress and anxiety would be immense, potentially leading to social unrest and political instability. It's important to remember, however, that this is just one potential scenario. The actual consequences of a Yellowstone supereruption would depend on a number of factors, including the size and intensity of the eruption, the prevailing weather patterns, and the level of preparedness of the global community. While the possibility of a Yellowstone supereruption is certainly cause for concern, it's also important to keep things in perspective. These events are rare, and the chances of one occurring in our lifetimes are relatively low. However, that doesn't mean we should ignore the risk. On the contrary, it's essential that we continue to monitor Yellowstone's activity, improve our understanding of supervolcanoes, and develop strategies to mitigate the potential consequences of a future eruption. The more prepared we are, the better we will be able to cope with whatever the future may hold. We can take comfort in the fact that scientists are diligently working to keep a watchful eye on this slumbering giant beneath the ground. All right, let's talk about the ash. When a supervolcano like Yellowstone erupts, it doesn't just spew lava. Think of it more like a colossal shotgun blast of rock, gas, and, most significantly, for our purposes, ash. And we're not talking about the kind of ash you get from a fireplace. This is volcanic ash, tiny shards of glass and pulverized rock. Incredibly abrasive and surprisingly heavy. The sheer volume of ash produced by a Yellowstone supereruption is almost incomprehensible. We're talking about potentially hundreds of cubic kilometers of the stuff, blanketing vast swaths of the continent. Picture this: a thick, choking cloud erupting skyward, driven by unimaginable force. Then imagine that cloud collapsing, spreading outwards in all directions, driven by the wind and its own immense weight. What happens when this ash falls to Earth? Well, the consequences are devastating, and they cascade across multiple systems. Let's start with the immediate environmental impact. For hundreds of miles around the eruption, plant life will be obliterated. The ash layer will smother vegetation, blocking sunlight and preventing photosynthesis. The weight of the ash can also crush smaller plants and break branches on larger trees. Entire ecosystems will be buried and suffocated. Water sources will become contaminated. Rivers, lakes, and reservoirs will be choked with ash, rendering them undrinkable for both humans and animals. The abrasive nature of the ash will also damage water treatment facilities. Further exacerbating the problem, agriculture will be decimated. Crops will be destroyed. Livestock will be poisoned by ingesting ash-contaminated feed, and farmland will be rendered unusable for years, perhaps even decades, depending on the thickness of the ash layer. This is not just a local problem. It's a national and potentially global food security crisis. The ripple effects on food prices and availability would be enormous. But the environmental impact is only part of the story. The infrastructure damage is equally catastrophic. Let's start with transportation. Roads will become impassable. Even a relatively thin layer of ash can make driving extremely hazardous, reducing visibility to near zero and creating slick, treacherous conditions. Heavier ashfalls will completely bury roads, rendering them unusable until they can be cleared. A monumental task in itself. Air travel will grind to a halt. Volcanic ash is incredibly damaging to aircraft engines. The tiny particles can melt inside the turbine blades, causing engine failure. Following even smaller volcanic eruptions, airspaces are closed for hundreds of miles around the affected area. A Yellowstone supereruption would likely ground air traffic across much of North America and potentially disrupt global air travel for weeks or even months. Power grids will be crippled. Ash accumulation on power lines and transformers can cause short circuits and power outages. The weight of the ash can also cause power lines to sag and break, leading to widespread blackouts. Restoring power to affected areas would be a slow and painstaking process. Communication networks will be disrupted. Ash can clog and damage telecommunications equipment, disrupting phone lines, internet access, and cellular service. This would hamper emergency response efforts and further isolate affected communities. Buildings will be at risk of collapse. The weight of accumulated ash on roofs can cause them to collapse, especially on structures not designed such loads. This is a particular concern for older buildings and those in areas with heavy snowfall, where the combined weight of ash and snow could be overwhelming. Water and sewage systems will fail. Ash can clog pipes and pumps, disrupting water supply and sewage treatment. This would create unsanitary conditions and increase the risk of waterborne diseases, and the economic consequences. Staggering. We're talking about trillions of dollars in damage, not just the immediate costs of cleanup and repair, but the long-term economic impact of lost productivity, business closures, and reduced tourism. The insurance industry would be overwhelmed, and the national economy would likely face a severe recession. Beyond the immediate damage, the ashfall would have long-term health consequences. The fine particles of volcanic ash are incredibly irritating to the respiratory system. Inhaling ash can cause coughing, wheezing, shortness of breath, and exacerbate existing respiratory conditions like asthma and bronchitis. Prolonged exposure to volcanic ash can lead to more serious lung diseases, such as silicosis. Eye irritation is another common problem. The abrasive nature of the ash can scratch the cornea, causing pain, redness, and blurred vision. People with contact lenses would be particularly vulnerable. The mental health impacts would also be significant. The stress and trauma of experiencing a supereruption, coupled with the disruption of daily life and the loss of homes and livelihoods, could lead to widespread anxiety, depression, and post-traumatic stress disorder. Cleaning up the ash would be a massive undertaking. It would require a coordinated effort involving government agencies, private contractors, and volunteers. The sheer volume of ash would pose a logistical challenge, and disposal sites would need to be carefully selected to avoid contaminating water supplies. The entire landscape would be reshaped. The ash layer would alter drainage patterns, change soil composition, and affect plant growth for decades to come. The eruption would leave an indelible mark on the environment, a stark reminder of the power of nature. So, the ash fall from a Yellowstone supereruption isn't just a nuisance. It's a catastrophic event with far-reaching consequences. It's a threat that we need to take seriously, and it underscores the importance of continued research and monitoring of Yellowstone's volcanic activity. While predicting the exact timing of an eruption is impossible, understanding the potential impact is crucial for developing effective mitigation strategies and protecting communities at risk. And when we come back, we will continue our journey with how this event could have long-term effects on climate change. Now, let's turn our attention to a chilling prospect: climate change and how a major eruption at Yellowstone could not just exacerbate existing problems, but trigger potentially long-term, even irreversible, shifts in the global climate system. This isn't just about a temporary volcanic winter, though that's certainly a part of the story. It's about the complex interplay of ash, aerosols, and greenhouse gases, and the cascading effects they could have on our planet's delicate balance. The immediate aftermath of a Yellowstone supereruption would, of course, be dominated by the volcanic winter phenomenon. Massive quantities of ash and sulfur dioxide would be blasted into the stratosphere. This high-altitude ash cloud would then spread across the globe, reflecting incoming solar radiation back into space. The result: a significant drop in global temperatures. Historical eruptions like Mount Tambora in 1815, which led to the year without a summer, provide stark reminders of this potential. Crops fail, growing seasons disappear, and widespread famine can occur. But here's where the story gets more complex, and where the connection to long-term climate change becomes particularly relevant. The sulfur dioxide injected into the stratosphere reacts with water vapor to form sulfuric acid aerosols. These aerosols are much finer than ash particles, and they can remain suspended in the atmosphere for months, even years, continuing to reflect sunlight and cool the planet. The duration and intensity of this cooling period would depend on the magnitude of the eruption and the amount of sulfur dioxide released. Some models suggest that a Yellowstone-scale eruption could trigger a cooling period lasting several years, potentially offsetting some of the warming caused by anthropogenic greenhouse gases. Now, on the face of it, a temporary global cooling might seem like a welcome reprieve in our warming world, a band-aid on a wound that needs stitching. However, such a rapid and drastic change in temperature could have devastating consequences for ecosystems and human societies already struggling to adapt to climate change. The abrupt shift could disrupt established weather patterns, leading to more extreme weather events like droughts, floods, and heat waves in some regions, while other areas experience prolonged cold spells. Agriculture would be thrown into chaos, and food security would be severely threatened. Think of the delicate balance of ecosystems, finely tuned over decades, even centuries, suddenly, violently disrupted. And that's not all. The injection of massive quantities of aerosols into the stratosphere could also affect atmospheric chemistry. These aerosols can act as surfaces for chemical reactions, potentially leading to increased ozone depletion. The ozone layer, of course, is vital for protecting us from harmful ultraviolet radiation from the sun. A thinning of the ozone layer could have serious consequences for human health and the environment, increasing the risk of skin cancer and damaging plant life. But perhaps climate change is its potential to disrupt carbon cycles. Volcanic eruptions release significant amounts of carbon dioxide, a major greenhouse gas, into the atmosphere. While the cooling effect of ash and aerosols might initially mask this effect, the long-term consequences could be significant. The added carbon dioxide could contribute to further warming once the aerosols have settled out of the atmosphere, essentially accelerating the pace of climate change in the long run. Moreover, a supereruption could trigger feedback loops within the Earth's climate system that further amplify warming. For example, a volcanic winter could lead to increased ice and snow cover, reflecting more sunlight back into space and further cooling the planet. However, this increased ice cover could also trap methane, a potent greenhouse gas, in permafrost, and hydrates. As the climate warms, this methane could be released into the atmosphere, accelerating warming even further. It's a complex web of interconnected processes, a precarious balancing act where one event can trigger a chain reaction with far-reaching consequences. Consider also the potential impact on ocean currents. The North Atlantic Current, for instance, plays a crucial role in regulating temperatures in Europe. A significant cooling event caused by a Yellowstone eruption could disrupt this current, leading to colder temperatures in Europe and potentially impacting weather patterns across the northern hemisphere. Changes in ocean temperature and salinity could also affect the ocean's ability to absorb carbon dioxide from the atmosphere, further exacerbating climate change. Furthermore, a Yellowstone eruption could release other greenhouse gases, such as nitrous oxide, which is even more potent than carbon dioxide. The release of these gases could contribute to long-term warming and further destabilize the climate system. It's like adding fuel to a fire, pushing the planet further away from a stable climate state. It is crucial to remember that the Earth's climate system is incredibly complex, and the exact consequences of a Yellowstone supereruption on long-term climate change are difficult to predict with certainty. However, the potential for such an event to trigger significant and potentially irreversible changes is very real. A Yellowstone eruption is not just a geological hazard. It's a potential climate hazard as well. Therefore, it is absolutely essential that we continue to study Yellowstone, to monitor its activity, and to improve our understanding of the potential impacts of a future eruption. This includes investing in climate modeling to assess the long-term consequences of such an event. And, perhaps more importantly, we must also take action to mitigate the risks of climate change by reducing our greenhouse gas emissions. The more we can reduce our reliance on fossil fuels and transition to a cleaner, more sustainable energy future, the better prepared we will be to weather any future climate shocks. Whether they come from natural events like a Yellowstone eruption, or from our own actions. The story of Yellowstone and climate change is a stark reminder of the interconnectedness of our planet and the importance of responsible stewardship. We must recognize that the choices we make today will shape the climate of tomorrow, and that we have a responsibility to protect our planet for future generations. The slumbering giant beneath Yellowstone serves as a powerful symbol, a reminder of both the awesome power of nature and the fragility of the Earth's climate system. It's a call to action, a plea for us to act responsibly and to safeguard our planet from the worst effects of climate change. Because when the Earth moves, the whole world feels it. And when a supervolcano awakens, the ripple effects could echo for centuries to come. So, let's turn our attention to the potential ramifications for us. For humanity, if the unthinkable were to occur. It's easy to get lost in the spectacular scale of a supervolcano eruption. The mind-boggling amounts of ash, the potential for global cooling. But behind all the scientific data and geological jargon lies a stark reality. Such an event would have devastating and long-lasting effects on human society, our economies, and even our collective psyche. Let's start with the social impact. Imagine, if you will, a significant eruption occurs at Yellowstone. Immediately, a vast area surrounding the caldera would become uninhabitable, coated in potentially feet of ash. Cities like West Yellowstone, Gardner, and others within a radius of several hundred miles could face near total devastation. This would trigger a massive displacement of people. We're talking about hundreds of thousands, potentially millions, seeking refuge in unaffected areas. This sudden influx of refugees would place immense strain on the resources of surrounding states. Food, water, shelter, medical care, all would be in desperately short supply. We'd likely see significant social unrest as communities struggle to cope with the overwhelming need. Competition for scarce resources could lead to conflict, and the breakdown of social order would be a very real possibility beyond the immediate impact zone. The effects would ripple outwards. Ashfall would disrupt transportation networks across vast swaths of the United States and potentially into Canada and Mexico. Air travel would be severely curtailed, if not completely grounded, for weeks or even months. Road and rail transport would be hampered by poor visibility and the sheer weight of the ash. Collapsing roofs and clogging infrastructure. Think about the implications for supply chains. Suddenly, the intricate network that brings us food, fuel, medicine, and all the necessities of modern life is crippled. Supermarkets would empty quickly, shortages would become widespread, and the cost of essential goods would skyrocket. Manufacturing would grind to a halt, further exacerbating the economic crisis. And that brings us neatly to the economic impact. The cost of a Yellowstone supereruption would be astronomical, dwarfing even the most devastating natural disasters in recent history. Direct damage to infrastructure, buildings, roads, power grids, water systems would run into the trillions of dollars. The disruption to trade and commerce would trigger a global recession, potentially a depression. The agricultural sector would be particularly vulnerable. Ashfall would contaminate crops, poison livestock, and disrupt planting cycles. The resulting food shortages would have a devastating impact on global food security, potentially leading to famine in some parts of the world. The insurance industry would likely collapse under the weight of the claims, further destabilizing the financial system. But beyond the immediate physical and economic consequences, there's a less tangible but equally important aspect to consider: the psychological impact. A supervolcanic eruption would be a truly terrifying event, a stark reminder of the power and unpredictability of nature. The constant ashfall, the disruption to daily life, the fear of the unknown, all would take a heavy toll on our mental health. Imagine the anxiety, the stress, the sense of helplessness that people would feel. The trauma of witnessing such devastation could have long-lasting effects, particularly on children. Trust in institutions could erode as people question the ability of governments and scientists to protect them. The spread of misinformation and conspiracy theories would further exacerbate the situation. In times of crisis, people often turn to alternative sources of information, and the internet can become a breeding ground for false or misleading claims. This can lead to confusion, mistrust, and even panic, making it even more difficult to coordinate an effective response. Furthermore, the sheer scale of the disaster could lead to a sense of collective despair. People might feel overwhelmed, hopeless, and unable to cope with the challenges ahead. This could lead to social isolation, a breakdown of community bonds, and a general sense of apathy. But it's not all doom and gloom. While the potential consequences are undeniably dire, it's important to remember that humanity is remarkably resilient. Throughout history, we've faced countless challenges, and we've always found ways to adapt and overcome them. In the face of a Yellowstone supereruption, we would need to draw on our collective strength, our ingenuity, and our compassion. International cooperation would be essential, as countries would need to work together to provide aid, share resources, and coordinate the recovery effort. The scientific community would play a crucial role in monitoring the volcano, providing accurate information, and developing strategies to mitigate the risks. Engineers would need to find innovative ways to clear ash, repair infrastructure, and build resilient communities. Healthcare professionals would need to provide mental health support and address the physical needs of the affected population. Ultimately, our ability to cope with a supervolcanic eruption would depend on our willingness to learn from the past, to prepare for the future, and to work together as a global community. It would require a fundamental shift in our thinking, from a focus on short-term gains to a long-term perspective that prioritizes sustainability and resilience. The potential impact on humanity is considerable, but by fostering resilience in our infrastructure, supply chains, and communities, we can greatly reduce the impact of any supervolcano event. All right. So we know that Yellowstone is a sleeping giant, a geological marvel, and a potential source of global disruption. But it's not all doom and gloom. There are real, tangible steps we can take to mitigate the risks and enhance our resilience in the face of a potential eruption. This isn't about panic. It's about preparedness, proactive measures, and understanding the science so we can make informed decisions. Let's start with the most obvious: monitoring. We've already touched on the incredible network of sensors that constantly monitor Yellowstone's activity. Seismographs track ground tremors, GPS stations measure ground deformation, and gas sensors analyze the composition of volcanic gases released from vents and hot springs. This data is invaluable, providing scientists with a real-time picture of what's happening beneath the surface. But it's not enough to just collect data. It's about analyzing it effectively and communicating the findings to the public in a clear and understandable way. That's where public awareness campaigns come in. Education is key. The more people understand about the risks, the better prepared they will be to respond appropriately. This includes teaching basic volcano safety, like knowing the evacuation routes, understanding the potential hazards of ashfall, and having an emergency plan in place. Think of it like fire drills. We practice them not because we expect a fire every day, but because we want to be ready if one ever happens. Now, let's talk about ashfall. This is arguably the most widespread and immediate threat from a Yellowstone eruption. A thick blanket of ash can disrupt transportation, contaminate water supplies, collapse roofs, and damage crops. So, what can we do about it? Well, one crucial step is developing robust ashfall forecasting models. These models use meteorological data and eruption scenarios to predict the likely path and thickness of ash plumes, allowing authorities to issue timely warnings and targeted advisories. Beyond forecasting, we need to focus on infrastructure protection. This means reinforcing roofs of critical buildings, developing ash removal strategies for airports and transportation networks, and stockpiling essential supplies like masks, air filters, and water purification systems. For agriculture, it may involve covering crops, providing alternative feed for livestock, and developing methods for cleaning ash-contaminated fields. Then there's the communication infrastructure itself. A major eruption could disrupt power grids and communication networks, making it difficult to disseminate information and coordinate emergency responses. Therefore, investing in redundant communication systems like satellite phones and backup power generators is crucial. Establishing predetermined communication protocols and designated channels for emergency information can also help to streamline the flow of information during a crisis. But preparation isn't just about the immediate aftermath. Long-term resilience is equally important. This involves developing strategies to minimize the economic and social impacts of a large eruption. One area of focus is diversifying the economy. Relying too heavily on a single industry, like tourism, can make a region particularly vulnerable to a volcanic event. Encouraging the growth of other sectors, like technology or manufacturing, can help to create a more resilient and diversified economic base. Another aspect of long-term resilience is ensuring adequate insurance coverage. Many standard homeowner policies don't cover volcanic eruptions, so people need to be aware of their coverage options and consider purchasing additional insurance to protect their property. Governments can also play a role by providing financial assistance to affected communities and businesses, helping them to rebuild and recover. On a larger scale, geological engineering, while still largely theoretical for something of Yellowstone's size, does offer some intriguing long-term possibilities. One concept involves controlled extraction of geothermal energy to slowly reduce the pressure within the magma chamber. This is a very long-term, speculative idea, and would require incredibly careful monitoring and management to avoid triggering an eruption. But it's an area of research that could potentially offer a way to mitigate the risks over centuries. Another avenue for research involves understanding the fundamental processes that trigger eruptions. What are the critical thresholds that need to be crossed for an eruption to occur? What are the early warning signs that can reliably predict an eruption? Answering these questions requires a multidisciplinary approach involving geologists, geophysicists, chemists, and computer scientists. International collaboration is also essential. Volcanic eruptions are global events with far-reaching consequences. Sharing data, expertise, and resources can help to improve our understanding of volcanic hazards and enhance our ability to respond effectively. International research projects can also facilitate the development of standardized monitoring protocols and eruption forecasting models. Finally, let's not forget the human element. A major volcanic eruption can have profound psychological impacts on individuals and communities. Providing mental health support and counseling services is crucial for helping people cope with the stress, anxiety, and trauma associated with a volcanic event. Building community resilience through social support networks and local organizations can also help to foster a sense of unity and shared purpose in the face of adversity. So, to recap, preparations and mitigation strategies for a potential Yellowstone eruption involve a multifaceted approach: enhanced monitoring, public awareness campaigns, infrastructure protection, ashfall forecasting, communication, resilience, economic diversification, insurance coverage, geological engineering research, international collaboration, and mental health support. It's a long list, I know. But each of these steps plays a vital role in reducing the risks and enhancing our ability to withstand the impact of a supervolcanic event. It's about understanding the science, taking proactive measures, and building a resilient society that is prepared for whatever the future may hold. It is, after all, the only home we know. So, as we grapple with the sheer magnitude of Yellowstone's potential impact, it's natural to wonder, are we just sitting ducks, waiting for the inevitable? Thankfully, the answer is a resounding no. A global network of dedicated scientists and engineers are constantly working to improve our ability to monitor Yellowstone, understand its behavior, and, ultimately, provide as much advance warning as possible should a major eruption become more likely. And it's fascinating to consider the innovative tools and research efforts being poured into this endeavor. One of the most significant advancements in recent years has been the expansion and refinement of seismic monitoring networks. Yellowstone is already one of the most seismically active regions in the United States, experiencing thousands of earthquakes every year. While most of these are small, they provide invaluable data about the movement of magma and fluids beneath the surface. By deploying a denser network of seismometers, including both surface-based and borehole instruments, scientists can detect even the faintest tremors, pinpoint their locations with greater accuracy, and build a more detailed picture of the subsurface plumbing system. Think of it like listening to the Earth's heartbeat. The more sensitive our instruments, the better we can understand its rhythms and detect any subtle changes that might indicate unrest. But seismic activity is just one piece of the puzzle. Ground deformation, or changes in the shape of the Earth's surface, is another key indicator of volcanic activity. As magma accumulates beneath the surface, it can cause the ground to bulge upward, like a balloon being inflated. Conversely, if magma is withdrawn or the magma chamber deflates, the ground can subside. To track these subtle movements, scientists rely on a technique called interferometric synthetic aperture radar, or INSAR. INSAR uses radar satellites orbiting the Earth to measure the distance between the satellite and the ground with incredible precision, down to just a few millimeters. By comparing radar images taken at different times, scientists can create detailed maps of ground deformation, revealing areas that are rising or falling. This data provides a crucial insight into the dynamics of the magma system and helps to identify areas that may be under increasing stress. Imagine having the ability to see the Earth breathing, expanding, and contracting in response to the forces at play beneath the surface. That's essentially what INSAR allows us to do, beyond seismic and deformation monitoring. Scientists are also employing a range of other advanced technologies to study Yellowstone. One increasingly important area is gas monitoring. Volcanoes release a variety of gases, including carbon dioxide, sulfur dioxide, and water vapor. By measuring the composition and flux of these gases, scientists can gain insights into the temperature, pressure, and chemical composition of the magma beneath the surface. Sophisticated gas sensors, deployed both on the ground and on aircraft, are being used to continuously monitor Yellowstone's gas emissions. Changes in gas composition or flux can be an early warning sign of increasing volcanic activity, like taking the volcano's temperature and checking its vital signs, providing a glimpse into its internal state. Another promising area of research is the study of hydrothermal activity. Yellowstone is famous for its geysers, hot springs, and mud pots, which are all manifestations of the vast hydrothermal system beneath the surface. This system is driven by heat from the magma chamber, and changes in the hydrothermal activity can reflect changes in the underlying volcanic system. Scientists are using a variety of techniques to monitor hydrothermal activity, including thermal infrared imaging, which measures the temperature of the ground surface, and chemical analysis of water samples, which reveals the composition of the hydrothermal fluids. This information can help to identify areas where the hydrothermal system is becoming more active or unstable, potentially indicating an increased risk of volcanic activity. Furthermore, advanced modeling techniques are playing an increasingly important role in understanding Yellowstone's behavior. Scientists are using sophisticated computer models to simulate the flow of magma, the deformation of the ground, and the release of gases. These models are based on our current understanding of the physics and chemistry of volcanic systems, and they are constantly being refined as new data becomes available. By running these models, under different scenarios. Scientists can explore the potential outcomes of different volcanic events and assess the likelihood of each scenario. It's like having a virtual Yellowstone, where we can experiment with different conditions and see how the volcano responds. All of this data from seismic networks, INSA, our measurements, gas monitoring, hydrothermal studies, and advanced modeling, is being integrated into comprehensive monitoring systems that provide a real-time assessment of Yellowstone's volcanic status. These systems are operated by the Yellowstone Volcano Observatory, a collaborative effort between the U.S. Geological Survey, the University of Utah, and the National Park Service. The observatory is responsible for monitoring Yellowstone's volcanic activity, conducting research, and communicating information to the public. And, speaking of the public, improved communication strategies are a crucial part of the early warning system. Should signs of escalating unrest be detected, it's vital that the public is informed quickly and accurately. The Yellowstone Volcano Observatory is working to improve its communication channels. Using websites, social media, and public briefings to keep the public informed about Yellowstone's status. Educational programs are also being developed to help people understand the risks associated with living near a supervolcano and to prepare for potential emergencies. Now, it's important to emphasize that despite all of these advancements, predicting volcanic eruptions remains a significant challenge. Volcanoes are complex systems, and their behavior can be difficult to predict. However, the progress that has been made in recent years is truly remarkable. Thanks to these new technologies and research efforts, we have a much better understanding of Yellowstone than ever before. While we cannot guarantee that we will be able to predict the next eruption with certainty, we are significantly better equipped to monitor the volcano, assess the risks, and provide as much advance warning as possible. The ongoing commitment to research and development in this area is essential. By continually pushing the boundaries of our knowledge and improving our monitoring capabilities, we can reduce the risks associated with Yellowstone and ensure the safety of the millions of people who live and visit this incredible natural wonder. The future of Yellowstone monitoring is bright, with exciting new technologies on the horizon. From drone-based remote sensing to artificial intelligence-powered data analysis. And who knows what groundbreaking discoveries await us as we continue to unravel the secrets of this sleeping giant dot. So, we arrive at a pivotal question, doesn't we? What truly determines whether Yellowstone will remain dormant? A geothermic wonderland humming beneath our feet, or unleash its immense power in another cataclysmic eruption? The answer, of course, is complex, a delicate interplay of geological forces that scientists are working tirelessly to understand. One of the most critical factors is the pressure within the magma chamber itself. Imagine it as a giant soda bottle, vigorously shaken. The more gas dissolved within a magma, primarily water vapor and carbon dioxide, the greater the potential for an explosive eruption. As magma rises closer to the surface, the pressure decreases, causing these gases to come out of solution, forming bubbles. These bubbles expand rapidly, and if the magma is viscous or sticky like peanut butter, they struggle to escape. This creates a tremendous buildup of pressure, eventually leading to a powerful eruption. Now, a magma chamber that is still quite far from the surface and contains relatively small amount of gas is less likely to erupt explosively. But pressure alone isn't the whole story. The composition and temperature of the magma are equally crucial. Magma that is rich in silica, the main component of quartz, tends to be more viscous. Think of honey versus water. Honey is much stickier and resists flowing. This stickiness traps gases more effectively, increasing the explosive potential. Conversely, magma that is hotter and less rich in silica is more fluid, allowing gases to escape more easily, leading to a less explosive, effusive eruption. Like those seen in Hawaii, another key factor is the roof rock, that solid layer of rock that sits above the magma chamber. This roof rock acts as a lid, containing the immense pressure below. The strength and integrity of this roof rock are paramount. If the roof rock is fractured or weakened by geological processes, it becomes easier for magma to find a pathway to the surface. This fracturing can be caused by a variety of factors, including tectonic stresses, hydrothermal activity, and even the slow, relentless creep of the surrounding crust. Now, tectonic stresses. Yellowstone sits in a tectonically active region, influenced by the movement of the North American plate and the underlying hotspot. These plate movements can create faults and fractures within the crust, providing pathways for magma to migrate upwards. Earthquakes, as we'll discuss further on, are a direct result of these tectonic stresses and can play a significant role in triggering volcanic eruptions. A large earthquake near Yellowstone could potentially destabilize the roof rock, allowing magma to reach the surface. Hydrothermal activity, the circulation of hot water through the Earth's crust, also plays a crucial and sometimes counterintuitive role. Yellowstone is famous for its geysers, hot springs, and fumaroles, all manifestations of this hydrothermal system. While these features are beautiful and fascinating, they also represent a continuous process of weakening the surrounding rock. The hot, acidic water dissolves minerals, creating underground cavities and weakening the overall structure. However, hydrothermal activity can also act as a release valve, allowing some of the pressure from the magma chamber to dissipate slowly, potentially preventing a more violent eruption. It's a delicate balance, this simmering cauldron of geothermal energy. And what about external factors? Could things like climate change, glacial melt, or even human activity influence Yellowstone's volcanic behavior? The short answer is maybe. Climate change is causing significant changes in the water cycle, with increased rainfall and snowmelt in some areas. This extra water could potentially seep into the ground, altering the pressure within the hydrothermal system and potentially affecting the stability of the crust. Glacial melt, the shrinking of glaciers, can also reduce the weight on the Earth's surface, leading to uplift and changes in stress patterns that could influence volcanic activity. The effects of this are still under investigation. Human activity, such as geothermal energy extraction or large-scale fluid injection, could also potentially have an impact, although the scale of these activities is currently relatively small compared to the immense forces at play beneath Yellowstone. However, it's crucial to proceed with caution and carefully monitor any potential consequences of human intervention. So, what about factors that prevent an eruption? Well, the continuous monitoring of Yellowstone's activity by the USGS and other scientific organizations is crucial. They track ground deformation, gas emissions, seismic activity, and temperature changes, providing valuable insights into the state of the magma chamber. This monitoring allows scientists to detect any signs of increasing unrest early on, potentially providing time for mitigation measures and public warnings. Furthermore, the natural cooling and crystallization of the magma chamber over time can also reduce the likelihood of an eruption. As magma cools, it solidifies, releasing gases and decreasing the overall pressure. This process can take thousands or even millions of years, but it represents a slow and gradual decline in the potential for a major eruption. And what if magma begins to move towards the surface? Not all magma intrusions result in eruptions. Sometimes magma can stall at depth, cooling and solidifying without ever reaching the surface. This can occur if the magma encounters impermeable rock layers or the pressure is insufficient to overcome the surrounding resistance. Ultimately, predicting the future behavior of a supervolcano like Yellowstone is an incredibly complex and challenging task. It involves integrating data from multiple sources, developing sophisticated computer models, and constantly refining our understanding of the underlying geological processes. While we cannot eliminate the risk of a future eruption, continued research and monitoring are essential for improving our ability to assess the threat and prepare for any potential consequences. It's a continuous quest for knowledge, a deep dive into the Earth's hidden secrets, all in the name of understanding and protecting ourselves from the immense power that lies beneath our feet. Now, let's turn our attention to something that often gets people worried when it comes to Yellowstone: earthquakes. The earth trembling beneath our feet can be a little unnerving, and naturally, we want to know what all that shaking means for the possibility of an eruption. Is every tremor a sign that the sleeping giant is about to awaken? Well, the short answer is no. But as always, with complex geological systems, the long answer is a little more nuanced. Earthquakes and volcanic activity are intimately linked, almost like two dancers in a very slow, very powerful ballet. In a volcanic region like Yellowstone, earthquakes are not just random occurrences. They're often signals of what's happening deep underground within the magma chamber and the surrounding crust. To understand this relationship, we need to appreciate the forces at play. Think of Yellowstone's magma chamber as a vast reservoir of molten rock, sitting several kilometers beneath the surface. This chamber isn't entirely liquid. It's more like a slushy mixture of molten rock, crystals, and dissolved gases. The pressure within this chamber is immense. These forces, combined with the internal pressure from the magma chamber, create a highly dynamic and unstable environment. Earthquakes occur when the stress in the rocks exceeds their strength, causing them to fracture and slip along fault lines. In volcanic areas, this stress can be caused by several factors. One of the most common is the movement of magma itself. As magma rises through the crust, it pushes against the surrounding rocks, creating stress and potentially triggering earthquakes. These earthquakes are often relatively small and localized, and they can occur in swarms, with dozens or even hundreds of small tremors happening over a period of days or weeks. Another cause of earthquakes in volcanic regions is the movement of fluids, like water and volcanic gases. Yellowstone is famous for its hydrothermal features: geysers, hot springs, and fumaroles, which are powered by the heat and fluids from the underlying magma chamber. These fluids circulate through the porous rocks and fractures and changes in their pressure or flow can also trigger earthquakes. Imagine the rocks as being like a sponge filled with water. If you squeeze the sponge, it might crack. Similarly, changes in the pressure of the fluids within the rocks can cause them to fracture and slip, leading to seismic activity. Now, it's important to distinguish between different types of earthquakes in a volcanic region. Tectonic earthquakes, which are caused by the movement of tectonic plates, can occur anywhere, including in volcanic areas. These earthquakes are often larger and more widespread than volcanic earthquakes, and they're not necessarily related to volcanic activity. In Yellowstone, most of the earthquakes are actually tectonic in origin, reflecting the ongoing tectonic activity of the region. Volcanic earthquakes, on the other hand, are directly related to the volcanic system. These earthquakes can provide valuable information about what's happening beneath the surface. For example, an increase in the frequency or intensity of volcanic earthquakes might indicate that magma is rising closer to the surface, or that the pressure within the magma chamber is increasing. Scientists carefully monitor these earthquakes to look for patterns and trends that could indicate changes in the volcanic system. One of the most useful tools for monitoring volcanic earthquakes is a network of seismometers. These sensitive instruments can detect even the smallest tremors, allowing scientists to track seismic activity in real time. By analyzing the location, depth, and magnitude of earthquakes, scientists can create detailed maps of the underground structure and identify areas of potential concern. Now, here's the crucial part. Just because there are earthquakes in Yellowstone doesn't mean an eruption is imminent. Yellowstone experiences thousands of earthquakes every year, most of which are too small to be felt by humans, are a normal part of the region's geological activity, and they don't necessarily indicate that an eruption is on the way. In fact, in many ways, these small, frequent earthquakes are a good thing. They help to release stress and prevent the buildup of pressure that could lead to a larger, more dangerous event. It's almost as if the Earth is taking small, regular breaths, preventing a single, explosive exhale. Think of it like a pressure cooker. If you release the pressure slowly and steadily, you can prevent a dangerous buildup. Similarly, the small earthquakes in Yellowstone help to release the stress in the rocks and prevent the magma chamber from becoming pressurized. However, it's essential to remember that Yellowstone is a dynamic and potentially hazardous system. Scientists are constantly monitoring the region for any signs of unusual activity, including changes in earthquake patterns, ground deformation, and gas emissions. These parameters, when combined, give scientists the best picture of what is happening deep below. A sudden increase in earthquake activity, especially if accompanied by other signs of unrest, could indicate that something is changing in the volcanic system. In summary, earthquakes are a normal and essential part of Yellowstone's geological activity. They provide valuable information about what's happening beneath the surface, and they help to release stress and prevent the buildup of pressure. While earthquakes can be unsettling, they don't necessarily mean that an eruption is imminent. Scientists are constantly monitoring seismic activity in Yellowstone to ensure that we have early warning of any potential changes in the volcanic system. So, The next time you hear about an earthquake in Yellowstone, remember that it's just one piece of a much larger puzzle. It's a reminder that Yellowstone is a living, breathing landscape, constantly evolving and changing beneath our feet. And by understanding the relationship between earthquakes and volcanic activity, we can better appreciate the complex and fascinating world that lies beneath the surface. Now, let's delve into a factor of immense significance when we're considering Yellowstone's temperamental nature: the relentless, grinding forces of tectonic plate movements. You see, Yellowstone isn't just sitting on a random patch of earth. It's strategically positioned atop a particularly dynamic geological intersection. And the stresses arising from this location play a crucial role in dictating the volcano's behavior. To truly grasp this, we need to rewind a bit and think about the grand planet-spanning picture of plate tectonics. Our Earth's outer shell, the lithosphere, isn't one continuous piece. Instead, it's fragmented into a mosaic of massive plates that are constantly, albeit incredibly slowly, shuffling across the surface. These plates, some carrying continents, others bearing vast ocean floors, interact in a few fundamental ways. They collide, they slide past each other, or they pull apart. And it's at these boundaries, these zones of intense interaction, where we find the vast majority of our planet's volcanoes and earthquakes. Now Yellowstone, rather uniquely, sits far away from any of these major plate boundaries. You won't find it nestled along the Ring of Fire, where the Pacific Plate is subducting, diving beneath other plates, causing that infamous chain of volcanoes. Instead, Yellowstone is situated smack dab in the middle of the North American plate. So, what gives? Why is it still such a hotbed of volcanic activity? Well, the answer lies in a fascinating geological feature known as a hotspot. Think of it as a fixed plume of molten rock or magma that rises from deep within the Earth's mantle, far below the lithosphere. This plume punches its way through the overlying plate, creating volcanic activity on the surface. Unlike volcanoes, at plate boundaries, which are relatively stationary, a hotspot remains fixed in place, while the plate above it slowly drifts along as the North American plate migrates over the Yellowstone hotspot. It leaves a trail of volcanic breadcrumbs in its wake. Over millions of years, this movement has created a chain of extinct volcanoes stretching across the Snake River Plain in southern Idaho. Yellowstone, in essence, is the current location of the hotspot, the most recent point of intense volcanic activity in this ongoing geological drama. But how do the plate movements directly influence Yellowstone's volcanic behavior? The answer is complex and multifaceted. First, The very act of the plate moving over the hotspot can affect the stress regime in the crust. The weight of the plate, combined with the upward pressure from the rising magma plume, creates a complex interplay of tension and compression. This, in turn, can influence the pathways that magma takes as it rises towards the surface. Fractures and faults within the crust created by the shifting plate can either facilitate the ascent of magma, leading to eruptions, or impede it, causing magma to pool and accumulate in the subsurface. Furthermore, the orientation and direction of plate movement can affect the shape and size of the magma chamber beneath Yellowstone. As the plate moves, it can stretch and deform the crust, altering the geometry of the magma reservoir and potentially triggering changes in its pressure and stability. Consider, for example, the role of earthquakes. While Yellowstone is famously a volcano, it's also prone to frequent seismic activity. Most of these earthquakes are relatively small, but they are an integral part of the overall system. Many of these tremors are triggered by the movement of magma and hydrothermal fluids beneath the surface. But some are also directly related to the broader stresses induced by the movement of the North American plate. These tectonic earthquakes, even those relatively far from Yellowstone, can act as a kind of geological nudge, influencing the stability of the magma chamber. A large earthquake could potentially trigger a release of pressure within the chamber, leading to an eruption. Alternatively, it could fracture surrounding rocks, allowing magma to escape more gradually, potentially leading to a period of increased hydrothermal activity, like more frequent geyser eruptions. In short, the tectonic plate movement isn't just a backdrop to Yellowstone's volcanic activity. It's an active participant in the drama. It shapes the stress field within the crust, influences the geometry of the magma chamber, and can trigger seismic events that, in turn, affect the stability of the volcanic system. It's a complex and intricate dance between the deep-seated forces of the Earth's mantle and the slow, relentless grind of the plates on the surface. It is important to note that while the movement of the North American plate is a critical factor, it is not the only one at play. Yellowstone's volcanic behavior is also influenced by factors such as the composition and volume of the magma, the rate at which magma is supplied from the mantle, and the properties of the surrounding rocks. Understanding the interplay between all of these factors is crucial for accurately assessing the risks posed by this incredible supervolcano. So, while we monitor the magma and the hydrothermal activity, and even the ground deformation, we also keep a watchful eye on the tectonic forces at play, the slow, imperceptible, yet ultimately powerful movements that can awaken a sleeping giant. Yellowstone, as we've explored, is a colossal heat engine. A geothermal powerhouse unlike almost any other on Earth. While the thought of a supereruption might understandably dominate the headlines, that immense subterranean heat reservoir also presents an opportunity. Geothermal energy, the very forces that could, hypothetically, reshape continents, could also provide clean, sustainable power to homes and businesses. It's a delicate dance, a balancing act between potential risk and potential reward. So, how do we harness this geothermal energy? And more importantly, how do we do it safely, minimizing the risk of upsetting the delicate balance of the Yellowstone ecosystem, or worse, triggering any kind of volcanic activity? The concept itself, it's relatively straightforward. Geothermal power plants tap into underground reservoirs of hot water or steam. This steam, or the steam created by flashing hot water, then spins turbines connected to generators, producing electricity. It's essentially the same principle as a coal-fired power plant, only instead of burning fossil fuels, we're using the Earth's internal heat. The challenge with Yellowstone isn't the availability of heat, it's abundant. The challenge is access and control. We can't simply drill anywhere we please. The park's unique geological environment and environmental regulations place significant restrictions on where and how geothermal exploration and development can occur. Existing geothermal plants operate outside the immediate boundaries of Yellowstone National Park, in areas where the geological risks are deemed lower and the potential environmental impact is more manageable. But even these existing plants require careful monitoring and management. One of the primary concerns is induced seismicity. Geothermal operations often involve injecting water into the ground to enhance steam production. This injection can, in some cases, lubricate existing faults, potentially triggering small earthquakes. While these earthquakes are usually minor, they highlight the need for meticulous geological surveys, sophisticated monitoring systems, and careful operational protocols. The U.S. Geological Survey, USGS, and other scientific organizations play a crucial role in monitoring geothermal areas and assessing the risk of induced seismicity. They use networks of seismometers to detect even the smallest tremors, allowing them to track changes in seismic activity and adjust operational parameters accordingly. Think of it as carefully listening to the Earth's heartbeat, paying close attention to any subtle changes in rhythm beyond the risk of induced seismicity. There are also environmental considerations. Geothermal fluids can contain dissolved minerals and gases, including hydrogen sulfide and mercury, which can be harmful if released into the environment. Modern geothermal power plants employ advanced technologies to capture and treat these fluids, preventing them from contaminating the air or water. This often involves re-injecting the cooled geothermal water back into the ground, a process that not only helps to maintain reservoir pressure, but also minimizes the potential for environmental pollution, another important aspect of responsible geothermal development is the preservation of Yellowstone's unique hydrothermal features. Geysers, hot springs, and mud pots are not only stunning natural wonders, but they also support a diverse range of extremophile organisms, microbes that thrive in extreme environments. Geothermal development must be carefully managed to avoid depleting the hot water supply that feeds these features, ensuring that these delicate ecosystems are not disturbed. The long-term sustainability of geothermal resources is also a key consideration. Geothermal reservoirs are not infinite. They can be depleted if extraction rates exceed recharge rates. Sustainable geothermal development requires careful management of reservoir pressure, fluid flow, and temperature. This often involves using advanced modeling techniques to simulate reservoir behavior and optimize production strategies. It's about striking a balance between energy production and resource conservation, ensuring that future generations can also benefit from Yellowstone's geothermal potential. So, what does the future hold for geothermal energy at Yellowstone? While large-scale geothermal development within the park remains unlikely due to environmental concerns, there is growing interest in exploring enhanced geothermal systems, EGs, outside park boundaries. EGS involves creating artificial geothermal reservoirs by fracturing hot, dry rock and injecting water to create steam. This technology could potentially unlock vast geothermal resources that are currently inaccessible using conventional methods. However, EGS also poses significant technical and environmental challenges. The fracturing process can potentially induce larger earthquakes, and the long-term sustainability of artificial reservoirs is still uncertain. Further research and development are needed to address these challenges and ensure that EGs can be implemented safely and responsibly. The potential benefits of geothermal energy are undeniable. It's a clean, renewable energy source that can help to reduce our reliance on fossil fuels and mitigate climate change. But with any technological advancement, caution and careful consideration of potential impacts are paramount. Yellowstone's geothermal power requires a delicate and informed approach, one that prioritizes environmental protection and scientific understanding. It's a long-term commitment, a continuous process of monitoring, evaluation, and adaptation. The goal is not simply to extract energy, but to do so in a way that is sustainable, responsible, and respectful of the natural wonders that make Yellowstone so unique. It's a challenge, certainly, but one that is potentially well worth the effort. For the promise of clean energy sourced directly from the earth beneath our feet is an alluring prospect. And, of course, the scientific insights gained from carefully studying the geothermal activity around Yellowstone have the potential to significantly advance our broader understanding of volcanology and geothermal resource management around the world. The knowledge we gain here, carefully, thoughtfully, can benefit us all. Now, shift our focus from the earth-shattering potential of a supereruption to something altogether more intimate, something almost miraculous, flourishing in the very heart of Yellowstone's volatile landscape. I'm talking about life. Not just any life, but life adapted to thrive in conditions that would be lethal to almost everything else on our planet. We're going to delve into the extraordinary realm of extremophiles, organisms that have carved out an existence in Yellowstone's geothermally heated springs, pools, and vents. Imagine a place where the water is scalding, often reaching boiling point, where the pH is either incredibly acidic, like battery acid, or extremely alkaline, like concentrated cleaning solution, where heavy metals and toxic chemicals are abundant. Sounds inhospitable, doesn't it? A place where even the toughest bacteria would struggle. Well, for extremophiles, this is paradise. This is home. These remarkable creatures, mostly single-celled organisms like bacteria and archaea, have evolved unique adaptations that allow them to not only survive, but actually thrive in these seemingly impossible environments. They hold secrets to the very origins of life on Earth, and potentially life beyond our planet. Let's start with the famous hot springs, like Grand Prismatic Spring, a swirling masterpiece of color. Those vibrant hues aren't just due to minerals in the water. They're a result of the different species of thermophiles, heat-loving organisms that inhabit different temperature zones within the spring. As the water cools from the center outwards, different communities of bacteria and archaea take over, each with its own unique pigment. For instance, Thermus aquaticus, a bacterium discovered in Yellowstone's mushroom spring, is perhaps the most famous extremophile of all. This tiny organism is the source of Taq polymerase, a heat-stable enzyme used in PCR, polymerase chain reaction, a revolutionary technique in molecular biology. PCR allows scientists to make millions of copies of a specific DNA sequence, and it's used in everything from disease diagnosis to forensic science. Without Thermus aquaticus, much of modern biotechnology wouldn't be possible. And it all started with a trip to a seemingly insignificant hot spring in Yellowstone. It's almost humbling, isn't it? To think that such a profoundly important tool for understanding life comes from life thriving in such an extreme place. But it's not just the heat that these organisms have adapted to. Many of Yellowstone's geothermal features are highly acidic. Take, for example, the mud volcano area, where bubbling mud pots and fumaroles release volcanic gases, creating highly acidic conditions. Here, you'll find acidophiles, organisms that love acid. These remarkable microbes have evolved mechanisms to pump protons, the very particles that make a solution acidic, out of their cells, maintaining a stable internal pH. They also have specialized enzymes and proteins that can function under incredibly harsh conditions. Consider the archaea, a domain of single-celled organisms distinct from bacteria and eukaryotes. Many archaea are extremophiles, and they're particularly abundant in Yellowstone's acidic hot springs. These resilient organisms have adapted to thrive in environments where most other life forms would simply dissolve. Their cell membranes are made of unique lipids that are resistant to the corrosive effects of acid, and their DNA is protected by specialized proteins. And then there are the organisms that tolerate incredibly alkaline conditions. In some of Yellowstone's springs, the water is highly alkaline, with a pH approaching that of household bleach. These alkaliphiles have evolved mechanisms to cope with a high concentration of hydroxide ions, which can damage cellular components. They often have specialized transport systems that allow them to maintain a stable internal pH, and enzymes that function optimally in alkaline conditions. But the adaptations of Yellowstone's extremophiles go beyond just temperature and pH tolerance. Many of these organisms are also resistant to heavy metals, such as arsenic and mercury, which are abundant in the park's geothermal features. They have evolved mechanisms to detoxify these metals, either by converting them into less toxic forms or by sequestering them within their cells. These extremophiles are not just fascinating organisms in their own right. They also play important roles in the park's ecosystems. They form the base of the food chain in many geothermal features, providing sustenance for other organisms, such as insects and crustaceans that have also adapted to these extreme conditions. Furthermore, the study of extremophiles has profound implications for our understanding of the origins of life on Earth. Some scientists believe that life may have originated in hydrothermal vents, similar to those found in Yellowstone in the early Earth. These vents would have provided a source of energy and nutrients, as well as protection from the harsh conditions on the early Earth's surface. By studying extremophiles, we can gain insights into the conditions that may have allowed life to arise in these environments. And it's not just about the origins of life on Earth. Extremophiles also provide clues about the possibility of life on other planets. Many of the conditions found in Yellowstone's geothermal features are similar to those found on other celestial bodies, such as Mars and Europa, one of Jupiter's moons. If life can thrive in these extreme environments on Earth, it's conceivable that it could also exist on other planets or moons with similar conditions. In fact, scientists are actively searching for evidence of life on Mars and Europa, and the study of extremophiles is playing a crucial role in this search. By understanding how life can adapt to extreme conditions, we can better identify potential habitats for life beyond Earth and develop strategies for detecting it. So, the next time you think of Yellowstone, don't just picture geysers and bison. Remember the hidden world of extremophiles, the tiny organisms that thrive in the most inhospitable environments. They are a testament to the resilience and adaptability of life, and they hold clues to the origins of life on Earth and the possibility of life beyond our planet. They are a reminder that even in the shadow of a supervolcano, life finds a way. And, perhaps, a little encouragement for us all to find our own ways to thrive, no matter the challenges we face. And so, we arrive at the grand question: what does the future hold for Yellowstone? Predicting the long-term evolution of a supervolcanic system is a task fraught with uncertainty, like trying to forecast the weather 1,000 years from now. But by combining our understanding of its geological history, current activity, and the fundamental processes that drive volcanism, we can paint a picture, albeit a hazy one, of what Yellowstone might look like millennia down the line. One thing we can say with relative confidence is that Yellowstone will continue to be a geologically active region. The heat source beneath the surface, the plume of magma rising from deep within the earth, isn't going anywhere anytime soon. This means that geysers will continue to erupt, hot springs will continue to bubble, and the ground will continue to subtly rise and fall. Yellowstone's geothermal features are a direct manifestation of this underlying heat, a constant reminder of the powerful forces at play beneath our feet. But what about the big one? The supereruption that captures headlines and fuels nightmares. The probability of another caldera-forming eruption on the scale of the Huckleberry Ridge, Mesa Falls, or Lava Creek events in the foreseeable future is statistically low. Geological timescales are vast, and these massive eruptions are separated by hundreds of thousands, even millions of years. However, low probability doesn't mean no probability. Scientists use a variety of methods to assess the likelihood of future eruptions, including monitoring ground deformation, analyzing gas emissions, and studying seismic activity. The subtle rising and falling of the Earth's surface can indicate changes in magma pressure beneath the caldera. Increased gas emissions, particularly sulfur dioxide and carbon dioxide, can suggest that magma is rising closer to the surface. And seismic activity, of course, can provide clues about the movement of magma and the potential for fracturing and faulting by analyzing these data. Scientists can identify areas of increased volcanic unrest. However, it's important to remember that unrest doesn't necessarily mean an eruption is imminent. Yellowstone has experienced periods of increased activity in the past that have not resulted in major eruptions. These periods of unrest can be caused by a variety of factors, including changes in hydrothermal activity, the movement of fluids within the Earth's crust, or even minor adjustments in the magma system. One of the biggest challenges in predicting Yellowstone's future is understanding the complex interplay between magma, water, and rock within the volcanic system. Yellowstone is essentially a giant hydrothermal system with vast amounts of water circulating through the fractured rock beneath the surface. This water is heated by the underlying magma and can create intense pressure. If this pressure builds up too much, it can trigger steam, explosions, or even hydrothermal eruptions, which can be significant events in their own right, although much smaller than a supereruption. Over the long term, the volcanic system will likely continue to evolve. The magma chamber beneath Yellowstone is not a static entity. It's constantly being replenished by magma rising from below, and it's also losing heat and crystallizing. Over time, the composition of the magma may change, and the way it interacts with the surrounding rock may also evolve. One possibility is that the magma chamber could gradually cool and solidify, eventually rendering Yellowstone inactive. This is a natural process that happens to all volcanoes eventually. However, given the immense size of the magma chamber and the continuous supply of heat from below, this process is likely to take many millions of years. Another possibility is that Yellowstone could continue to experience smaller eruptions, such as lava flows or ash falls, without ever experiencing another caldera-forming supereruption. These smaller eruptions could still have significant local impacts, but they wouldn't have the same global consequences as supererupts. It's also possible that Yellowstone could eventually experience another caldera-forming eruption, perhaps triggered by a change in the magma supply, a major earthquake, or some other unforeseen event. While the probability of this happening in our lifetimes is very low, it's important to be prepared for the possibility. Ultimately, the future of Yellowstone is uncertain. It's a dynamic and complex system that is constantly evolving. But by continuing to study and monitor Yellowstone, we can improve our understanding of its behavior and better assess the risks it poses beyond the threat of eruptions. Yellowstone's geothermal activity also presents opportunities. Geothermal energy is a clean, renewable source of power that could help reduce our reliance on fossil fuels. Yellowstone's vast geothermal resources could potentially be harnessed to generate electricity. But this must be done carefully to minimize the risk of disrupting the natural environment. Moreover, Yellowstone is a unique and valuable ecosystem that is home to a diverse array of plant and animal life, including many rare and endangered species. Protecting this ecosystem is essential. Regardless of the volcanic risks, sustainable tourism and careful resource management are key to ensuring that Yellowstone remains a treasure for future generations. Looking far into the future, imagine Yellowstone National Park, perhaps unrecognizable to us. Imagine geothermal plants nestled carefully into the landscape, drawing energy from the earth without disrupting its natural wonders. Imagine scientists continuing to monitor the park's activity, not with fear, but with fascination and respect for the powerful forces at play. Imagine future generations marveling at the geysers and hot springs, learning about the park's volcanic history, and appreciating the delicate balance between geological power and ecological beauty. Yellowstone is a reminder that our planet is a dynamic and ever-changing place. It's a place of immense power and beauty, a place where the forces of nature are on full display. By understanding and respecting these forces, we can learn to live in harmony with our planet and ensure a sustainable future for ourselves and for generations to come. The story of Yellowstone is far from over. It's a story that is still being written, one eruption, one geyser, one scientific discovery at a time. And it's a story that will continue to captivate and inspire us for centuries to come. And so, we arrive at a pivotal point in our exploration of Yellowstone, a point where we shift from the realm of potential catastrophe to the domain of human potential. While the prospect of a supereruption understandably evokes a sense of unease, even dread, it's crucial to remember that our understanding of Yellowstone is not just about calculating risk. It's also about cultivating curiosity and championing environmental stewardship. The very act of studying Yellowstone, acute of meticulously monitoring its every tremor and thermal anomaly, is a testament to our inherent human drive to understand the world around us. It's a thirst for knowledge that has propelled us from the caves of our ancestors to the forefront of scientific discovery. Each new data point, each refined model, each technological advancement brings us closer to unraveling the complex secrets hidden beneath Yellowstone's deceptively placid surface. Think about it. We are, in essence, listening to the Earth. We are using our ingenuity to translate the subtle murmurs of magma, the whispers of steam, and the groans of tectonic plates into a language we can understand. And in doing so, we are not only learning about Yellowstone. We are learning about the fundamental processes that shape our planet and, indeed, the entire cosmos. This pursuit of knowledge is not merely an academic exercise. It's a deeply empowering endeavor. By understanding the mechanisms at play, we can move beyond fear and towards informed decision-making. We can develop strategies for mitigation, for adaptation, and for resilience in the face of potential challenges. We can ensure that future generations are better equipped to navigate the complexities of living on a dynamic planet. But the story of Yellowstone is not just about science. It's also about our responsibility as stewards of the environment. Yellowstone National Park, a jewel in America's crown, is more than just a collection of geological features. It's a living ecosystem teeming with biodiversity and a place of profound natural beauty. The very processes that pose a potential threat, the geothermal activity, the volcanic forces, are also responsible for the unique and captivating landscapes that draw millions of visitors each year. Therefore, our approach to Yellowstone must be one of careful balance. We must strive to understand the potential risks while simultaneously protecting the delicate ecosystems that thrive within the park. We must ensure that our research efforts do not inadvertently disrupt the natural processes that we are seeking to understand. This requires a commitment to sustainable practices, to minimizing our impact on the environment, and to fostering a sense of respect for the natural world. It requires us to think critically about our own relationship with the planet and to recognize that our actions have consequences, both intended and unintended. Consider, for instance, the challenges associated with geothermal energy development. While harnessing Yellowstone's geothermal resources could potentially provide a clean and sustainable source of power, it also carries the risk of altering the park's hydrothermal systems, impacting geysers, hot springs, and the unique microbial life that depends on these features. Therefore, any geothermal development in the region must be approached with extreme caution, guided by rigorous scientific assessment and a commitment to minimizing environmental impact. Similarly, we must be mindful of the impact of tourism on Yellowstone's fragile ecosystems. While tourism provides economic benefits to the surrounding communities, it also places a strain on park resources contributing to pollution, habitat degradation, and the disruption of wildlife. Sustainable tourism practices, such as promoting responsible visitor behavior, investing in infrastructure improvements, and supporting local conservation initiatives, are essential for ensuring the long-term health of Yellowstone National Park. Ultimately, embracing environmental stewardship at Yellowstone means recognizing that we are not separate from the natural world. We are an integral part of it. Our actions have consequences, and our future is inextricably linked to the health and well-being of the planet. By fostering a sense of respect for the environment and committing to sustainable practices, we can ensure that Yellowstone remains a source of wonder and inspiration for generations to come. And, perhaps most importantly, understanding Yellowstone and other geological forces at play on our planet should lead us to a greater appreciation for the delicate balance of forces that make life on Earth possible. It is a reminder that our planet is a dynamic, ever-changing system, and that we are all interconnected. This understanding can inspire us to be more mindful of our impact on the environment and to work towards a more sustainable future for all. Let us, therefore, approach Yellowstone not with fear, but with a sense of curiosity and responsibility. Let us embrace the opportunity to learn from this extraordinary natural laboratory, to deepen our understanding of the Earth's processes, and to cultivate a more sustainable and harmonious relationship with the planet. Let the story of Yellowstone be a story of human ingenuity, environmental stewardship, and a commitment to building a better future for all. Because, in the end, it's not just about understanding a supervolcano. It's about understanding ourselves and our place in the grand tapestry of life on Earth. And so, we arrive at the culmination of our journey into the heart of Yellowstone, a place of immense power, hidden dangers, and breathtaking beauty, a landscape sculpted by forces far beyond human comprehension, reminding us of the raw, untamed energy that lies just beneath our feet. As we pull back the lens and zoom out for a moment, what can we truly say about Yellowstone's significance? What lasting impressions should we take with us? First and foremost, Yellowstone stands as a stark reminder of the Earth's dynamic nature. It's not a static, unchanging rock. It's a living, breathing entity, constantly evolving and reshaping itself. Mountains rise and fall, continents drift, and volcanoes awaken and slumber. Yellowstone is a concentrated, dramatic example of this constant flux, a place where we can witness the very forces that have shaped our planet for billions of years. It's a humbling realization that our existence, our cities, our entire civilization rests upon this volatile, ever-shifting foundation. Consider for a moment the sheer scale of geological time. We, as humans, operate on timescales of days, years, even a century feels like an eternity. But Yellowstone operates on timescales of millennia, even hundreds of thousands of years. Eruptions happen, magma chambers fill and empty, and the land slowly deforms, all at a pace that dwarfs our own fleeting existence. It forces us to confront our own insignificance in the face of these vast geological processes, a perspective that can be both unsettling and profoundly liberating. But it's not just about humbling us. Yellowstone also holds immense scientific significance. It's a natural laboratory, a place where scientists can study the inner workings of a supervolcano in real time. By monitoring the geysers, hot springs, ground deformation, and seismic activity, they can gain invaluable insights into the behavior of magma chambers, the triggers of eruptions, and the potential consequences of volcanic activity. The knowledge gained from Yellowstone is not just relevant to Yellowstone itself. It can be applied to understanding volcanoes around the world, helping us to better assess and mitigate volcanic hazards globally. And that brings us to the question that inevitably looms large in our minds: the potential for future eruptions. As we've explored, the possibility of another supereruption at Yellowstone is a very real one, albeit a statistically unlikely one in any given human lifetime. But the potential consequences of such an event are so catastrophic that it demands our attention and our preparation. It's easy to become fixated on the worst-case scenarios, on the images of ash clouds and global devastation. But fear alone is not a productive response. Instead, we must embrace a proactive approach, supporting scientific research, developing early warning systems, and implementing mitigation strategies to reduce the risks and enhance our resilience. And while the potential for a major eruption looms large, it's important to remember that Yellowstone is so much more than just a potential threat. It's also a place of incredible beauty and biodiversity. The geysers and hot springs are not just signs of volcanic activity. They are also unique ecosystems, teeming with life that has adapted to thrive in extreme conditions. From the thermophilic bacteria that paint the hot springs in vibrant colors to the hardy plants and animals that have carved out a niche in this harsh environment, Yellowstone is a testament to the resilience and adaptability of life itself. Furthermore, Yellowstone is a vital part of our natural heritage. It's one of the oldest and most iconic national parks in the United States, a place where millions of people come each year to experience the wonders of nature and to connect with the land. It's a place of inspiration, a place of recreation, and a place of solitude. It's a place that deserves our respect and our protection, not just for its geological significance, but also for its intrinsic value as a natural treasure. And let's not forget the indigenous peoples who have called this region home for thousands of years. Their deep connection to the land, their traditional knowledge of the environment, and their cultural heritage are an integral part of Yellowstone's story. It's important to acknowledge and respect their perspectives, to learn from their wisdom, and to ensure that their voices are heard in the management and preservation of this extraordinary place. In the end, Yellowstone is a complex and multifaceted entity, a place that embodies both the destructive and creative forces of nature. It's a reminder of our planet's power, a testament to the resilience of life, and a call to action to protect our natural heritage. It compels us to consider our place within the grand scheme of things, to acknowledge our vulnerability, and to embrace our responsibility as stewards of the earth. So, as you reflect on everything we've explored, I hope you'll carry with you a sense of awe and wonder, a healthy dose of respect for the power of nature, and a commitment to supporting the scientific research and conservation efforts that are so crucial to understanding and protecting this extraordinary place. Yellowstone, with all its fiery potential, ultimately reflects the broader story of our planet, a story of constant change, of dramatic events, and of the enduring power of life to adapt and thrive. It's a story that we are all a part of, and one that we must strive to understand and protect for generations to come. And perhaps, as we drift off into sleep, we can dream not of cataclysm, but of curiosity, of stewardship, and of the enduring beauty that can be found even in the face of the most formidable natural forces. The earth is alive, ever-changing, and Yellowstone serves as a constant, vital reminder of that fact. Sleep well, knowing that we are all connected to this dynamic, beautiful, and sometimes terrifying planet we call home.